Hello there, and welcome to the Drift to the Stars. I'm so glad you found your way here tonight. Wherever you are right now, whatever the day brought, whatever weight it left at your door, you can set it down. This is a quiet place, a slow place, a place where the universe opens gently, like a window at the end of a long day, and invites you to remember how vast and calm everything really is, underneath all the noise. Tonight, we are going to travel. Not quickly, not urgently. We are going to drift through some of the most beautiful, most quietly astonishing truths that science has uncovered about the cosmos and about the strange, tender fact of being alive inside it. Some of these things will make you feel wonderfully small. Others will make you feel, perhaps surprisingly, a little more at home. All of them are real. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, if you're ready, let's begin. There is something waiting for you in the space between your own atoms, if you're willing to sit with it. You are, in the most literal and astonishing sense, mostly empty. Not empty in a lonely way, not hollow, but the atoms that build your hands, your ribs, your quietly breathing chest, each one of them is almost entirely space. If you were to remove all that emptiness, all the void between the nucleus of each atom and the electrons drifting around it, every human being who has ever lived could fit inside a volume roughly the size of a sugar cube, a single sugar cube, and yet here you are, present, solid feeling, real. The emptiness is not absence, it is structure. It is the architecture of forces, electromagnetic, nuclear, that give shape to the illusion of solidity. The chair beneath you, the blanket across you, the floor below, all of that, none of it is truly touching anything. It is force, holding the appearance of contact together, distance, making itself feel like closeness. There is something quietly comforting in that. You are not a dense, fixed thing. You are more like a slow song, notes that do not touch each other, held together by the silence between them. And the universe, it turns out, is built the same way. Mostly space, mostly quiet. And somehow, against all odds, exactly enough. The universe has an edge you will never see, and that edge is not a wall. Picture yourself standing in a vast, ancient forest, looking outward through the trees. At some point, the light goes dim, not because there is a barrier, but because that is simply as far as the light reaches before the world bends out of view. The observable universe works something like that. In every direction you could point, there is a horizon, not a boundary, but a limit of what light has had time to carry to us. Beyond that horizon, space continues, possibly forever. We simply cannot see it yet. The universe is approximately 13.8 billion years old, but because space itself has been expanding the whole time, the observable universe stretches roughly 46 billion light-years in every direction, more than 3 times the age of the universe, expressed in distance. It is a quiet paradox that has no sharp answer, only a gentle dissolving of certainty. Scientists call this boundary the particle horizon. Everything beyond it is not gone, not forbidden. It is simply unreachable by light in the time that has been available. Those distant reaches may hold galaxies, stars, other versions of everything we know. We will never receive a signal from them. They are beyond the reach of even the oldest light. And still, knowing that, this sky above you tonight holds more than enough. The light that reaches you is ancient and real and traveled unimaginably far. That is not a small thing. It is a kind of gift. Your hands have never touched anything. Not once. Not ever. Hold that gently. Because it is not a trick. It is one of the most quietly strange facts in all of physics. When you press your palms together, what you are feeling is not contact. It is repulsion. The electrons on the surface of one hand push back against the electrons on the surface of the other, creating a force that the brain interprets as touch. The atoms themselves never meet. This has been understood since the early 20th century. Electron clouds, the The diffuse shells of negative charge surrounding every atom repel each other before they ever make true contact. Every handshake, every embrace, every time you have ever held someone, it was all electromagnetic repulsion, experienced as warmth and presence. And somehow, knowing that makes it more tender, not less. The sensation is real. The force is real. The warmth is real. What is extraordinary is that the universe built a system so precise, so finely tuned, that distance could be felt as closeness. That force could be felt as love. You have never touched the ground you walk on. You have never touched the cup you hold, and yet you are supported, held, carried. The universe keeps you at arm's length and calls it solid ground. There is a place in space so empty, it feels like a held breath. It is called the Botes Void, named for the constellation in whose direction we find it. And it is not merely empty in the way a room might be empty, or a field. It is empty on a scale that challenges something quiet in the mind. A region of space approximately 330 million light-years across, containing far fewer galaxies than the surrounding universe would lead us to expect. Where the cosmic web has filaments and clusters and nodes of galaxies, this region has almost none. Scientists are still not entirely certain how it came to be. The standard model of cosmic structure formation can produce voids, and does, but none quite so cleanly, so thoroughly sparse as the Boötes void. Some researchers think it may be the result of many smaller voids having merged over billions of years. Others are less certain. It remains one of those places where the universe seems to be doing something we have not fully decoded yet. What strikes most people, when they sit with it, is not the size, it is the quiet. A volume of space nearly 1/3 of a billion light-years wide, where very little has gathered, where matter chose to spread rather than cluster. A kind of cosmic rest, as if space, in one great region, decided not to hurry, decided simply to be still. You are resting tonight. So, quietly, is the Boötes void. The warmth on your face when you stand in sunlight is older than you might imagine. Not 8 minutes old, though that is true in its own way. The light takes about 8 minutes to travel from the sun's surface to your skin, but the energy carried by that light, the heat you feel, the brightness that closes your eyes, began its journey far earlier. Deep inside the sun's core, where hydrogen fuses into helium under pressure and temperature beyond anything on Earth's surface, a photon of light is born, and then it almost immediately collides with another particle, and another. The interior of the sun is so dense that a single photon can take anywhere from 10,000 to 100,000 years to work its way outward from the core to the surface, bouncing, being absorbed, being re-emitted, bouncing again, a slow, ancient stumble toward the light. When that photon finally reaches the sun's surface, the photosphere, it is free, and 8 minutes later, it is resting on your face. So the warmth you feel on a clear morning carries energy that was trapped in the sun before humans had language, before the first city, before the last ice age. It traveled for 100,000 years through the body of a star, and then 8 minutes through the void to find you. The sun has been patiently delivering these ancient parcels to your doorstep every single day of your life. And it will continue long after this quiet evening is over. There is a planet made of diamond, and it orbits a star that is already dead. It is called 55 Cancri by some, and there are others debated in the literature, but perhaps the most poetically apt is a world sometimes nicknamed the Diamond Planet, a carbon-rich world, where the pressure and temperature conditions may have compressed carbon into vast quantities of diamond beneath its surface. It orbits not a living star like our own sun, but a white dwarf, a star that has already exhausted its fuel and collapsed to a dense, slowly cooling remnant. The planet endures, compressed, quiet, brilliant in a way that no eye has ever seen and may never see. White dwarfs are what most stars, including our own sun, will eventually become. When a star like the sun runs out of hydrogen to fuse, It swells into a red giant, sheds its outer layers, and leaves behind a hot, dense core roughly the size of Earth. Over billions and billions of years, that core cools. Slowly. The timescale is so long that no white dwarf in the universe has yet had time to cool completely. They are all still warm, still faintly glowing, still carrying heat from lives they no longer live. And around one of them, a diamond world turns slowly in the dark, not lost, not forgotten by physics, simply waiting in the way that ancient, compressed things wait. Still, patient, harder than anything the Earth has made. You are not the same person who woke up this morning. Not entirely. This is not philosophy. It is biology, and it is happening right now, even as you rest. Every second, your body is replacing cells, millions of them, in a process so continuous and so quiet that you never feel it happening. The lining of your stomach renews itself roughly every few days. Your skin sheds and rebuilds over the course of weeks. Your red blood cells last about 4 months before being gently retired and remade. Even your bones, which feel so permanent, so fixed, are in a slow, constant conversation with themselves, dissolving and rebuilding, year after year. The timescales vary by tissue. Some cells last a lifetime. Neurons in certain parts of the brain, the lens of the eye, these tend to stay with you from birth. But much of what you think of as your body is a living renovation, always underway, never announced. What this means, quietly, is that the boundary between who you were and who you are is softer than it feels. You are not a fixed object moving through time. You are more like a river. The water changes, the banks shift slightly, and yet the river continues, recognizably itself, carrying the same name, the same direction, the same gentle sound. Even as you breathe slowly right now, something in you is being renewed. Something is being gently released. The body knows how to let go. It has always known. It does it without asking you. It does it while you sleep. The largest structure in the known universe looks like something you carry inside your skull. The cosmic web is the name scientists give to the vast architecture of matter stretched across the observable universe. Galaxies do not scatter randomly through space. They cluster along filaments, enormous strands of dark matter and gas that intersect at nodes and trail off into voids. Seen in simulation or in the maps astronomers have painstakingly assembled over decades, the cosmic web looks unmistakably like a neural network, like the branching, connecting, communicating structure of the human brain. The resemblance is not mystical. It is mathematical. Both structures emerge from similar underlying rules networks, where nodes connect, where density attracts more density, where the geometry of branching follows patterns that appear across many scales of nature. Rivers branch this way. Lightning branches this way. The vessels in a leaf branch this way. But the parallel between the cosmic web and the human brain remains one of the most quietly arresting images in modern science. Researchers have formally compared the two and found statistical similarities in their clustering and connectivity that are difficult to dismiss as coincidence of appearance. You contain, inside your head, an architecture that echoes the largest thing we know, not because the universe put it there intentionally, but because the same mathematics, the same deep logic of connection, runs through everything from the space between galaxies to the space between your thoughts. The universe is not outside you, looking in. It is continuous with you. You are one of the ways it folds back on itself and notices. On one of the inner planets, a day outlasts a year, and time itself seems to move differently. Venus is close to us, in cosmic terms, near enough to shine brilliantly in the evening sky, near enough that early astronomers imagined it might be something like Earth beneath its clouds. In one sense, it moves briskly. It completes a full orbit around the Sun in roughly 225 Earth days, a year shorter than ours. And yet Venus rotates so slowly on its own axis that a single Venusian day, the time from one sunrise to the next, lasts approximately 117 Earth days, longer than its own year. There is something else. Venus rotates backward compared to most planets in the solar system. If you could stand on its surface and watch the sky, the sun would rise in the west and set in the east, slowly, across a sky choked with thick sulfuric acid clouds, moving almost imperceptibly. Scientists are still not fully certain why Venus spins the way it does. Early collisions, tidal interactions with the sun, the thick atmosphere itself, all have been proposed. The answer is likely a combination, but the precise history is not yet settled. What remains is this: time is not a constant across the solar system. Every world keeps its own rhythm. Every planet is its own kind of clock, marking duration in a way that has nothing to do with ours. And somewhere in that thought is a loosening, a quiet reminder that the urgency of your own hours is local, particular, and very gently negotiable. Every atom in your body has lived many lives before it found its way to you. The carbon in your bones was fused inside a star that died billions of years before our sun was born. The oxygen you are breathing right now was made by ancient microbes and by stellar furnaces. The iron that colors your blood was forged in a supernova, a star so massive that when it exhausted its fuel, it collapsed and then exploded with a force that briefly outshone entire galaxies, scattering its contents across light years of space. Those contents drifted. Slowly, over millions of years, they gathered into clouds. The clouds collapsed under gravity into new stars, new planets. Some of that matter became the early Earth. Some of it became the ocean. Some became the first living things. Some became forests. Some became the food you ate as a child without knowing any of this was true. And now it is you, temporarily, beautifully, without any permanent claim. This is not a metaphor. It is the actual, traceable history of the matter you are made of. Carl Sagan said we are star stuff, and he was not reaching for poetry. He was stating the supply chain. You are borrowed material, on loan from the universe, arranged for a brief and specific time into the particular shape of you. When you breathe out tonight, some of those atoms begin their next journey. You are not holding them. You are simply, for now, the place they rest. The moon is leaving us, and it has been leaving us since before anything alive existed to notice. Each year, the moon drifts approximately 3.8 centimeters farther from Earth. That is the rate your fingernails grow. Slow, incremental, barely noticeable in any human lifetime, but accumulating over billions of years into a vast change. When the moon first formed, roughly 4.5 billion years ago, likely from the debris of a colossal collision between early Earth and a Mars-sized body, it was much closer. The tides it raised were enormous, crashing across a young planet, nothing like the one you rest on tonight. The mechanism is tidal friction. As the moon pulls on Earth's oceans, it creates a slight bulge that races ahead of the moon's position due to Earth's faster rotation. That bulge exerts a tiny gravitational tug on the moon, pulling it forward in its orbit, which causes it to spiral gradually outward. Energy transfers, slowly and continuously, from Earth's rotation to the moon's orbit. As a result, Earth's days are also getting very slightly longer, by about 1.4 milliseconds per century. Again, imperceptibly slow, but over billions of years, Earth once had days of only a few hours. There is something tender about all of this. The moon is not gone. It is not rushing. It is simply, incrementally, finding a slightly different place, drifting the way things drift when they have nowhere urgent to be, in all the quiet time the universe allows. The universe has a voice, if you know how to listen for it. It is not a sound, exactly, in the way that sound needs air to carry it. But embedded in the cosmic microwave background radiation, the faint glow of ancient light left over from roughly 380,000 years after the beginning of the universe, there are patterns, fluctuations in temperature, variations so slight they span only millionths of a degree, that encode the acoustic oscillations of the early universe. matter and energy, in those first moments, moved in waves, compressed and expanded, like the pressure waves of sound, but vast, and made of the universe itself. When scientists translate the mathematical structure of those oscillations into audible frequencies, the universe hums, a deep, low note, far below what human ears could detect. Without that translation, that corresponds to a specific resonant frequency of the early cosmos. NASA and other research groups have produced audio representations of this signal. It is not music that anyone composed. It is the fundamental tone of the universe, recorded in the oldest light we can detect, still washing over us in every direction right now, tonight, passing through the walls of whatever room you rest in. The universe sang before stars existed, before planets, before anything alive could hear. And the record of that song is still playing, faintly, across the whole sky, a lullaby so old it has no composer, and an audience that only recently learned it was listening. Some stars are so vast that to cross one would take longer than human civilization has existed. Our sun is not a small star, but it is not a large one either. It sits comfortably in the middle range, a yellow dwarf with a diameter of about 1.4 million kilometers, large enough to contain more than 1 million Earths. And yet there are stars that make our sun look like a pebble beside a house. The largest known stars, the red and yellow hypergiants, objects like UY Scuti or Stephenson 2-18, have radii estimated at somewhere between 1,500 and 2,000 times that of our sun. If one of these stars were placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. Light, traveling at the speed it always travels, would take several hours to cross from one side to the other. These stars do not live long. The more massive a star, the more furiously it burns, and the shorter its life. While our sun will burn steadily for about 10 billion years total, the largest stars may exhaust themselves in only a few million years, a cosmically brief, brilliant life, burning bright and dying young. And yet tonight, some of them are still out there, enormous, slowly pulsing. Surrounded by vast clouds of gas they have shed like old skin, ancient in human terms, though young in cosmic ones, burning quietly at distances so great that the light reaching your sky right now left those stars before your grandparents were born. Size, it turns out, is not the same as permanence. The universe knows this well. The color of your blood connects you to the death of a star. Iron is the element that gives hemoglobin its ability to carry oxygen through your body. It is also the element that ends a massive star's life. When a star large enough has spent its fuel fusing lighter elements, hydrogen into helium, helium into carbon, carbon into heavier and heavier atoms, it eventually reaches iron. And iron is where stellar fusion stops paying. Fusing iron consumes energy rather than releasing it. The star's core, suddenly unable to support itself, collapses in a fraction of a second. The outer layers crash inward and then rebound outward in a supernova explosion of almost incomprehensible energy. That explosion scatters iron across light years of space. Some of it, over millions of years, found its way into the cloud of gas and dust that became our solar system. Some of it settled into the forming Earth. Some of it dissolved into ancient oceans. Some of it was incorporated into the first living things that learned to use it. And eventually, through an unbroken chain of biology stretching across billions of years, some of it arrived in you. The iron in your blood, right now, the iron that carries oxygen to your brain as you drift towards sleep, was forged in a stellar explosion before our sun existed. A star died so that, among many other things, you could breathe. That is not a small exchange. It is perhaps the longest, most patient act of generosity in the known universe. And it is written, quietly and permanently, in the color red. Pluto has blue skies, and the discovery arrived like a quiet gift. When the New Horizons spacecraft made its close flyby of Pluto in July 2015, after traveling for 9.5 years across the solar system, it sent back images that surprised nearly everyone who saw them. Pluto's sky, in the direction away from the sun, is blue. Not the deep saturated blue of Earth's daytime sky, a softer, hazier blue, ringing the small world's thin atmosphere at the edges. The reason is a layer of haze composed of particles called tholins, complex organic molecules formed when nitrogen and methane in Pluto's atmosphere are broken apart by ultraviolet light from the sun and then recombine into larger structures. These particles are themselves reddish, which contributes to the coloring of Pluto's surface in places. But when sunlight scatters through them, the haze produces a blue tint, the same general optical phenomenon that gives Earth its blue sky, playing out on a tiny, frozen, distant world. Scientists had not confidently predicted this. The haze was known to likely exist, but its optical properties and the resulting sky color were not certain until the images arrived. Pluto is so far from the sun that sunlight there is roughly 1,000 times dimmer than on Earth. And yet, in that dim, ancient cold, the sky is blue. A pale, quiet, improbable blue, drifting with haze above plains of nitrogen ice and mountains of water ice at the edge of our solar system, in a dark we will likely not visit again for a very long time. Somewhere out there, a blue sky waits in the cold. It does not need to be seen to be real. The universe is not only growing, it is growing faster, pulled by something no one has yet named. In 1998, two independent teams of astronomers were studying distant supernovae, stellar explosions, used as reliable measuring sticks across cosmic distances, expecting to find that the universe's expansion was slowing down. Gravity, after all, pulls matter together. The assumption was that the expansion begun at the Big Bang would be gradually decelerating, like a ball thrown upward, eventually slowing under gravity's pull. Instead, both teams found the opposite. The most distant supernovae were dimmer than expected, meaning they were farther away than they should have been. The universe was not slowing, it was accelerating. The expansion was speeding up. This discovery, which earned a Nobel Prize in Physics in 2011, required the existence of something driving that acceleration, something with a repulsive effect at cosmological scales, something that fills all of space and grows stronger as space expands. Scientists named it dark energy, which is less a description than an admission. We know something is there, we can measure its effects, and we do not know what it is. Dark energy appears to make up approximately 68% of the total energy content of the universe, the largest ingredient of everything and the least understood. It is not a small gap in knowledge. It is a fundamental, honest, quietly humbling unknown at the very heart of cosmology. The universe is accelerating away from itself, driven by something vast and invisible, and still, genuinely, mysterious. There is something oddly comforting in that. Even the universe is still figuring itself out. A spoonful of the densest known matter would outweigh every mountain on Earth, gathered together. Neutron stars are what remains when a massive star, not quite massive enough to become a black hole, collapses at the end of its life. The collapse is so extreme that protons and electrons are forced together into neutrons, and the resulting object is packed to a density the everyday world has no reference for. A neutron star typically contains roughly 1 to 2 times the mass of our entire sun, compressed into a sphere perhaps 20 kilometers across, the size of a city. At that density, a teaspoon of neutron star material would have a mass of approximately 4 billion tons. The exact figure varies by the specific star and the models used, but the scale remains consistently, quietly staggering. Every mountain range on Earth, the Himalayas, the Andes, the Rockies, the Alps, all of them gathered and weighed a single small spoonful of neutron star outweighs that sum. Neutron stars also spin. Some of them spin very fast. A class of neutron stars called pulsars rotate hundreds of times per second, sweeping beams of radiation across space like the beam of a lighthouse, so regular that early researchers, when they first detected the signal in 1967, briefly and genuinely considered whether it might be a signal from an intelligent civilization. They called it LGM, one for a time, Little Green Men. It was not. But the impulse to wonder is not embarrassing. It was a reasonable response to a universe that keeps doing things no one expected. Somewhere in the universe, at every moment, a star is being born. Star formation happens inside cold, dense clouds of gas and dust called nebulae. Slowly, over millions of years, regions within these clouds become slightly denser than their surroundings. Gravity does the rest, pulling more gas inward, increasing the pressure and temperature at the center. When the core grows hot enough and dense enough, hydrogen begins to fuse into helium, and a star ignites. This is happening right now. Not hypothetically, not in some ancient past. In the Orion Nebula, visible to the naked eye as a smudge of soft light in the constellation Orion's sword, stars are actively forming tonight. In the Carina Nebula, in the Eagle Nebula, inside the famous pillars of creation imaged by Hubble, and later, in stunning new detail by the James Webb Space Telescope, in those pillars, towering columns of gas and dust light years tall, young stars are being born inside cocoons of material, not yet visible at optical wavelengths. Infrared images pierce the dust and reveal them warm, young, luminous, brand new to a universe that is 13.8 billion years old. The universe did not do all its creating at the beginning and then stop. It is still at it, right now, in the quiet dark above you, in clouds of gas drifting between stars. Something is crossing the threshold from cold and dark into warm and bright. Something is beginning. The universe has not finished. It is still making things, slowly, in the ancient dark, with no audience but the light itself. 2 small spacecraft, launched in the 1970s, are still going. They are the farthest human-made objects from Earth, and tonight they are moving through a region no probe has visited before. Voyager 1 and Voyager 2 were launched in 1977, within weeks of each other, on a trajectory that would take them past Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune as well. They used the gravitational fields of the outer planets as a kind of cosmic slingshot, gaining speed from each encounter and bending their paths outward toward the edge of the solar system and beyond. Voyager 1 crossed into interstellar space beyond the heliosphere, the bubble of solar wind that surrounds our solar system, in 2012, becoming the first human-made object to do so. Voyager 2 followed in 2018. Both spacecraft are still functioning, still sending data back to Earth, though it now takes more than 20 hours for a signal to make the journey at the speed of light. They carry golden records, discs containing sounds and images of Earth, greetings in 55 languages, music from many cultures, the sound of rain and surf and wind, a mother's first words to a newborn child, chosen carefully, curated lovingly, sent into space in the quiet hope that something, somewhere, might someday find them. No one knows if that will ever happen. The odds are very long. But tonight, moving through the cold and ancient darkness between stars, 2 small machines made by human hands are carrying the sound of your world outward, quietly, without stopping, still traveling, after nearly 50 years, through a dark no one has ever seen. Sleep may be the most ancient cosmic maintenance ritual your body performs. For most of human history, sleep was poorly understood. It looked like inactivity, a vulnerability, a pause in the useful work of being alive. But in recent decades, neuroscience has revealed something quite different. During sleep, particularly during certain stages of deep slow-wave sleep, the brain activates a system called the glymphatic system, a network of channels around the brain's blood vessels that, during sleep, expand and allow cerebrospinal fluid to flush through the brain's tissues, clearing out metabolic waste products that accumulate during waking hours. Among the substances cleared this way are proteins associated with neurodegenerative diseases. The brain, during sleep, is literally washing itself, cleaning out the residue of a day of thinking. Scientists are still mapping exactly how this process works, how much sleep is needed for it to be fully effective, And what goes wrong when it is repeatedly disrupted? The field is young, and the questions are genuinely open. But what is established is this: sleep is not passive. It is an active, essential biological process that the brain does on its own behalf when given the chance. Your body knows that rest is not laziness. It is maintenance. It is care. The brain waits for the quiet and then does something that cannot be done any other way. Even as you drift toward sleep right now, this ancient, tender process is beginning. The day's residue is being gently washed away. You are being cleaned by your own stillness, cared for by the dark, renewed by the simple act of letting go. Saturn's rings are younger than the dinosaurs, and they will not last forever. This came as a genuine surprise to planetary scientists. For a long time, the rings were assumed to be ancient relics of the solar system's formation, billions of years old, as permanent a feature as the planet itself. But data gathered by the Cassini spacecraft, which orbited Saturn from 2004 until its deliberate plunge into the planet's atmosphere in 2017, told a different story. By measuring the rate at which ring material is being drawn down into Saturn's upper atmosphere by a process called ring rain, where charged water particles from the rings follow magnetic field lines down into the planet, scientists estimated that the rings could disappear entirely within perhaps 100 million years. And working backward, the data suggested the rings likely formed somewhere between 10 and 100 million years ago. The dinosaurs were already walking the Earth 100 million years ago. Saturn's rings, those iconic, breathtaking, planet-girdling bands of ice and rock that have defined our image of that world for as long as humans have pointed telescopes at the sky, are geologically recent, temporary, a passing feature in a very long story. There is something quietly freeing in that. The things that seem most permanent, most definitively fixed, are often simply the things that change more slowly than we can perceive. The rings are leaving. Grain by grain, droplet by droplet, they are returning to the planet that spawned them, and for this particular sliver of cosmic time, we happen to be here to see them. That is not an accident to take lightly. It is, by any measure, an extraordinary piece of timing. The light arriving at your eye from the most distant galaxies has been traveling longer than Earth has existed. Our planet formed approximately 4.5 billion years ago from the cloud of gas and dust that surrounded the young sun. That is an enormous span of time by any human measure. And yet the observable universe contains galaxies so far away that the light we detect from them left its source more than 13 billion years ago, when the universe was only a few 100 million years old. The Earth did not exist yet. The sun did not exist. The atoms that would one day become you had not yet gathered. The James Webb Space Telescope has observed galaxies from when the universe was only about 300 million years old, a tiny fraction of its current age. These galaxies appear as they were in the universe's early childhood, and they have had 13 billion years to change since that light departed. What they look like now, we cannot say. We are seeing their past, pinned to the sky like an old photograph. Light carries information, and distance becomes time. Every object you look at in the night sky is a message from the past, arriving now. The nearest star beyond our sun, Proxima Centauri, shows you what it looked like a little over 4 years ago. The Andromeda Galaxy, visible to the naked eye as a faint smudge, shows you 2.5 million years in the past. And the faintest, most distant galaxies the Webb telescope can find show you the universe as a young thing, still finding its shape. The sky is not a snapshot of now. It is a layered archive of different moments, all arriving at your eyes simultaneously. You are always, when you look up, reading history. Beneath the forest floor, a conversation is always underway. The trees above ground, the ones you can see, whose canopies spread and whose bark you could touch, are only part of what a forest is. Below the surface, threading through the soil, in networks that can extend for hundreds of kilometers, a vast web of fungal filaments called mycelium, connects the roots of trees to each other and to the fungi that grow among them. This network, sometimes called the Wood Wide Web, facilitates the transfer of nutrients, sugars, water, and chemical signals between trees. Older, larger trees, sometimes called mother trees by researchers who study these systems, have been observed sending significantly more carbon through these networks to younger seedlings growing in their shade, particularly to seedlings of their own species. Trees under attack by insects release chemical signals that travel through the mycelium, and neighboring trees respond by increasing their own chemical defenses before they are attacked. Scientists are careful about the language they use here, whether this constitutes communication in any meaningful sense, whether the trees are doing something that deserves words like intention or awareness, remains genuinely debated. What is established is the transfer of material and signal, the measurable response of one organism to another, mediated by a third. The forest is a system. It is more connected than it appears. Even as you rest tonight, in whatever room holds you, a forest somewhere nearby is passing something through the dark slowly, chemically, quietly. Roots touching roots through a middleman made of thread. There are more possible games of chess than there are atoms in the observable universe. The number of atoms in the observable universe is estimated at roughly 10 to the power of 80. A very large number, written out, would fill many pages, and yet the number of possible distinct chess games, the Shannon number, named for mathematician Claude Shannon, who first estimated it, is approximately 10 to the power of 120, 40 orders of magnitude larger than the count of atoms in everything we can see. Chess was invented by humans. It has 8 rows, 8 columns, 32 pieces, and a set of rules a child can learn in an afternoon. And within those simple constraints, the space of possibility is larger than the observable universe contains, in discrete physical units. This is not because chess is complicated. It is because combination and sequence generate complexity at a rate that outruns physical scale almost immediately. The same principle underlies why no two snowflakes are identical, why genetic variation produces such staggering diversity from a 4-letter molecular alphabet, why the space of possible human thoughts and feelings may be effectively inexhaustible. Simplicity contains multitudes. The rules are small. The space they open is not. And somewhere in that thought is a gentle reminder that the interior of a human life, the combinations of memory and feeling and perception that make up a single evening, a single hour, a single drifting moment before sleep, is not a small or simple thing. Even if it feels quiet, even if it feels like nothing much is happening, something very large is always unfolding in something very small. The sun will one day expand and swallow the inner planets, and this too is a kind of peace. Approximately 5 billion years from now, the sun will have exhausted the hydrogen in its core. The fusion that has kept it burning steadily for 10 billion years will falter, and the core will begin to contract under gravity while the outer layers expand. The sun will swell into a red giant, growing to perhaps 100 times its current diameter, and the inner solar system will change beyond recognition. Mercury and Venus will almost certainly be consumed. Earth's fate is less precisely determined. Some models suggest Earth will be engulfed. Others suggest the sun may lose enough mass during the red giant phase that Earth drifts outward just enough to survive, though in a form so scorched and transformed it would bear no resemblance to anything living. 5 billion years is a number too large to feel. It exceeds the current age of the Earth. It exceeds the total lifespan of most stars. It is a duration in which anything we would recognize as human civilization is not a footnote but less than a footnote, an event so brief in that frame that no metaphor quite captures it. And in 5 billion years, whatever has become of life and mind and knowing in this corner of the galaxy, if anything has, they will watch a star do what stars do, quietly, over millions of years, blooming outward, fulfilling the slow arc of what it always was. Not an ending so much as a transformation. The sun returning its substance to space, seeding new clouds, new possibilities, new material for whatever the universe still wants to make. The end is a long way away. And it, too, is part of the story. A microscopic animal has survived open space, and it did so without asking permission. Tardigrades, sometimes called water bears or moss piglets, are 8-legged microscopic animals less than 1 millimeter long, found in mosses, lichens, soil, and ocean sediment on every continent, including Antarctica. They are not remarkable to look at, even under a microscope. They look a little like a stubby, slow-moving caterpillar with too many legs and a slightly confused expression. But tardigrades possess a biological capability unlike almost anything else known to science. When conditions become hostile, extreme dryness, extreme temperature, radiation, vacuum, they can enter a state called cryptobiosis. They retract their legs, expel nearly all the water from their bodies, reduce their metabolism to less than 0.01% of normal, and essentially pause. In this state, called a ton, they can survive temperatures close to absolute zero, temperatures above 150 degrees Celsius, pressures 6 times greater than the deepest ocean, and doses of radiation that would kill any other known animal. In 2007, and again in subsequent experiments, tardigrades were exposed to open space on the outside of orbiting spacecraft, including vacuum and unfiltered solar radiation. Many survived. They do not know they survived. They do not know they went to space. They are not heroes, in any sense they would recognize. They are simply, quietly, extraordinarily resilient. A reminder that life, wherever it has found a foothold, does not give it up easily. Life holds on. Life waits. Life finds a way to continue, in the ton, in the dark, until conditions ease, and it is time to unfold again. On one small world in our solar system, a day lasts twice as long as a year. Mercury is the closest planet to the Sun, and its relationship with time is genuinely strange. It completes one orbit around the Sun every 88 Earth days, a year brief enough that seasons, in any meaningful sense, do not exist. And yet, Mercury rotates so slowly on its own axis, once every 59 Earth days, that its relationship between its day and its year becomes unusual, in a way that took astronomers a while to fully work out. Because of the combination of Mercury's slow rotation and its relatively fast orbit, and because its orbit is notably elliptical rather than circular, a solar day on Mercury, the time from one sunrise to the next at any given point on the surface, lasts approximately 176 Earth days. 2 full Mercury years pass in the time it takes Mercury to complete one day. If you stood on Mercury's surface, you would watch the sun rise, move across the sky, briefly pause, and move slightly backward, then continue forward and set all over the course of what would feel, to your body, like half a year of continuous experience. And the sun would appear nearly 3 times larger than it does from Earth. Mercury also has the most eccentric orbit of any planet in the solar system, which is why Einstein's general theory of relativity was partly confirmed by correctly predicting Mercury's orbital behavior, something Newtonian gravity had failed to do. The smallest planet, closest to the Sun, helped confirm the deepest theory of space and time. Even the smallest things carry large truths, if you are patient enough to look carefully. 2 galaxies are falling toward each other across an ocean of space, and when they meet, almost nothing will be lost. The Milky Way and the Andromeda Galaxy are approaching each other at roughly 110 kilometers per second. This is not a new development. They have been moving toward each other for most of the universe's history, drawn together by mutual gravity across a distance of approximately 2.5 million light-years. Astronomers estimate they will begin their collision in about 4.5 billion years, a merger that will unfold across hundreds of millions of years after that. Slow and vast and unlike anything we have language for, and yet the word collision is misleading. Galaxies are not solid objects. They are enormous collections of stars, separated by distances so vast that the stars themselves almost never actually strike each other. When two galaxies merge, their stars pass through and around each other like two swarms of fireflies drifting through the same field on a summer night. The shapes of both galaxies will be dramatically distorted. Long tidal streams of stars will be flung outward. Eventually, over billions of years, the two will settle into a single, larger elliptical galaxy. Astronomers have already given it a name, Milkomeda. Our solar system will likely be flung into a different region of this new galaxy. The night sky, as seen from whatever remains of Earth, will transform over millions of years into something unrecognizable and extraordinary. Nothing will be destroyed. Everything will be rearranged. Two vast, ancient structures, each containing hundreds of billions of stars, moving toward each other not in violence but in the slow, inevitable way that massive things respond to gravity. The universe does not crash. It merges. It folds into new shapes. It continues, in a different form, as it always has. The air you breathe today was made by life, and life made it as a gift it never intended to give. For the first 2 billion years of Earth's history, the atmosphere contained almost no free oxygen. The early atmosphere was rich in nitrogen, carbon dioxide, methane, and other gases. But oxygen, the molecule your cells depend on with every breath, was essentially absent. Life existed in that early world, but it was microbial, anaerobic, and entirely unbothered by the lack of something it had never needed. Then, approximately 2.4 billion years ago, a group of microorganisms called cyanobacteria evolved the ability to perform oxygenic photosynthesis using sunlight to convert water and carbon dioxide into sugars and releasing oxygen as a byproduct. They did not do this to help future animals breathe. Oxygen was their waste product. They were, in effect, exhaling. But they exhaled for hundreds of millions of years, and oxygen accumulated in the atmosphere. This event, called the Great Oxidation Event, was catastrophic for many anaerobic organisms of the time, for whom oxygen was toxic. It was, from their perspective, a mass poisoning of the world they had lived in. And it was, from the perspective of everything that came later, an extraordinary gift. Every breath you draw tonight is the accumulated exhalation of billions of years of microscopic life. The oxygen filling your lungs right now was made by organisms that lived and died long before anything with eyes existed to see the sky they were slowly changing. You are breathing the ancient work of the very first living things, and they never knew you were coming. Some stars are so old they were burning before the galaxy that holds them existed. The star designated HD 140283 has been studied carefully for decades, and its estimated age has consistently come out at approximately 14 billion years older, on the face of it, than the current best estimate for the age of the universe itself, which sits at 13.8 billion years. This apparent contradiction caused considerable scientific discussion, and the resolution lies partly in measurement uncertainties on both sides. The star's age, when error bars are applied, is consistent with being nearly as old as the universe, formed in its very earliest period. It is sometimes called Methuselah's star, after the biblical figure said to have lived for centuries beyond ordinary human lifespan. And like its namesake, it seems to have endured while everything around it changed entirely. HD 140283 is a metal-poor star, meaning it contains very little of the elements heavier than hydrogen and helium. This is a fingerprint of extreme age. The first stars in the universe formed from only hydrogen and helium, because heavier elements had not yet been forged in stellar interiors and scattered by supernovae. Stars that formed very early therefore contain very little metal. HD 140283 carries that signature. It was there, burning, before the Milky Way had fully assembled itself around it. It is visible in the constellation Libra, close enough to be seen with a modest telescope, an ordinary-looking point of light that has been shining since the universe was in its infancy, patient, old beyond reckoning, still quietly fusing hydrogen in its core, surrounded now by a galaxy that formed around it while it burned. Inside the sun, a single particle of light wanders for 100,000 years before it ever sees the sky. The sun's core, where nuclear fusion occurs, is an environment of such extreme density that a photon produced there cannot travel in a straight line for more than a tiny fraction of a millimeter before colliding with another particle and being absorbed and re-emitted in a random direction. This process repeats over and over in what physicists call a random walk, a path with no direction, no intention, no destination in mind. The result is that energy produced in the sun's core takes an extraordinarily long time to work its way outward to the surface, a layer called the photosphere. Estimates vary depending on the model and the specific assumptions made, but the commonly cited range is between 10,000 and 100,000 years. Some models suggest it could be even longer. When a photon finally reaches the photosphere, it enters a region thin enough to escape freely, and then, in approximately 8 minutes, it crosses the 150 million kilometers between the sun and Earth. So the light warming your skin on any given afternoon has been on a journey of staggering patience, trapped for millennia inside a star, bouncing endlessly in the dark interior, until one day, by no decision of its own, simply by the slow accumulation of random steps, it found the surface, found the sky, found the long, clean, unimpeded path across space to wherever you happen to be standing. Every photon of sunlight is a traveler that waited longer than human civilization has existed for 8 minutes of freedom. The size of the universe is not the same as the age of the universe, and the difference is something the mind softly refuses to hold. The universe is approximately 13.8 billion years old. You might therefore expect the observable universe to extend 13.8 billion light-years in every direction. After all, light has had that long to travel, but the observable universe actually extends approximately 46 billion light-years from Earth in every direction. Its full diameter is around 93 billion light-years. The reason is that space itself has been expanding the entire time. When the earliest light now reaching us was emitted, the region of space it came from was much closer to us. But space has expanded in the billions of years that light has spent traveling, carrying the source of that light far beyond where it started. By the time the light arrives, the object that emitted it is now roughly 46 billion light-years away, even though the light only traveled 13.8 billion light-years in travel time. This is one of the places where the universe quietly declines to behave the way everyday intuition expects. Space is not a fixed container, with objects moving through it. Space itself stretches. Distances grow not because things are moving away from a center, but because the fabric between them expands. There is no center. There is no edge. Every point in the universe is equally the center of its own observable horizon. You are, in a precise and non-metaphorical sense, at the center of your own observable universe, not because you are special every point is, but because that is simply how an expanding universe works. Wherever you are, the cosmos extends equally, in all directions, as far as light has had time to carry news of it. You are surrounded, equally, by everything. Some mountains are still growing, and the earth beneath you has never finished becoming what it is. The Himalayas are the tallest mountains on Earth by elevation above sea level, and they are still rising. The Indian tectonic plate continues to push northward into the Eurasian plate at a rate of roughly 5 centimeters per year, about the speed at which your hair grows. The collision that built the Himalayas began approximately 50 million years ago, when what is now India, then an island continent drifting northward across the ancient Tethys Sea, made contact with Asia. The mountains rise, but they also erode. Wind, water, frost, and time work continuously at their summits and slopes, carrying material downward and eventually to the sea. The net change in elevation at any given time depends on the balance between uplift and erosion, and in the Himalayas today, uplift is winning, though only barely, and only for now. Other mountain ranges are sinking. The Appalachians, among the oldest mountain ranges on Earth, were once perhaps as tall as the Himalayas. Hundreds of millions of years of erosion have worn them down to the gentle, forested ridges they are today. Rounded, patient, ancient in a way the Himalayas are not yet. The ground beneath you is not still. It has never been still. It breathes on timescales too slow to feel, rises and falls and collides, and spreads in rhythms measured in tens of millions of years. The solid, dependable floor of your world is a slow and ancient dance, and you are resting on it tonight as it continues, quietly, without hurry, doing what it has always done. A bolt of lightning is 5 times hotter than the surface of the sun, and it lasts less than a second. The surface of the sun burns at approximately 5,500 degrees Celsius. It is the kind of heat that vaporizes most materials, that would reduce any solid thing to plasma in moments. And yet the channel of a lightning bolt, in the fraction of a second during which it exists, reaches temperatures of approximately 30,000 degrees Celsius, 5 times hotter than the solar surface, briefly, impossibly, in a jagged line carved through ordinary air. Lightning happens because of charge separation within storm clouds. Ice crystals and water droplets collide, transferring electrons in ways that build enormous electrical potential between the base of the cloud and the ground below. When the potential becomes large enough, the air, normally an excellent insulator, breaks down. A channel forms, branches, reaches toward the ground, and in an instant, billions of electrons cascade downward. The thunder you hear afterward is the sound of air expanding explosively around that channel as it superheats in microseconds. Sound moves more slowly than light, so you hear the aftermath of what your eyes already saw. The same storm clouds that carry lightning also carry rain, and rain is what fills rivers, feeds forests, fills reservoirs, and falls on the rooftops above sleeping children. The same sky that briefly burns hotter than the sun also delivers the water that keeps everything green and alive. The sky holds extremes in easy company. Violence and gentleness, heat and rain, brief and ancient, all moving together through the same quiet afternoon. The universe does not find this contradictory. Neither, in your depths, do you. Whales sing in frequencies so low the ocean carries their voices across entire ocean basins. The songs of blue whales and fin whales fall largely below the range of human hearing, without technological assistance. These are infrasonic calls, deep pulses and moans that travel through seawater with an efficiency that air cannot match. Water is denser than air, and sound moves through it nearly 5 times faster, and in some cases, much farther. In the deep sound channel, a layer of ocean at a particular depth, where temperature and pressure combine to create ideal acoustic conditions, low-frequency sounds can propagate for thousands of kilometers, with remarkably little loss of energy. Blue whales, the largest animals known to have ever existed on Earth, produce calls that can reach 188 decibels, among the loudest sounds made by any animal, and they produce them alone, and in patterns that repeat, that vary seasonally, that differ between populations. Scientists call them songs, because the repetition and structure warrant the word, though what the whales are communicating, precisely, remains an open question. What is known is that they are communicating across distances that dwarf any other animal communication on Earth. A blue whale singing in the North Atlantic may be heard, in the right conditions, by another whale thousands of kilometers away in the mid-Atlantic. They are talking across an ocean, slowly, in the dark, in frequencies your body can feel as vibration before your ears can process them as sound. Tonight, somewhere in the deep ocean, a whale is singing. The song is moving outward through cold, dark water, crossing distances that take light only milliseconds to cover, but carry the whale's voice with a patience and reach that feels almost deliberate, almost tender. The ocean listens, and somewhere another whale hears. On Mars, the sun sets blue, and the dust that colors the sky does so in reverse. On Earth, the sky is blue during the day because the atmosphere scatters shorter blue wavelengths of sunlight in all directions, filling the sky with scattered light, while longer red wavelengths pass more directly through. At sunset, when sunlight travels through more atmosphere at a low angle, the blue scatters away, and the longer red and orange wavelengths dominate, painting the horizon in warm colors. On Mars, the atmosphere is thin, less than 1% of Earth's atmospheric pressure, and it is laden with fine reddish dust particles. These particles are large enough and numerous enough to scatter light differently than Earth's gas molecules do. During the Martian day, the sky takes on a butterscotch or pale pink hue. The dust scatters red light preferentially, washing the daytime sky in muted amber. But at sunset, when sunlight angles through more of that dusty atmosphere, the blue and violet wavelengths that have been suppressed all day begin to dominate near the sun. The Martian sunset glows blue, a cool, pale, otherworldly blue that pools around the setting sun and fades into the pink-brown of the surrounding sky. Images returned by NASA rovers have shown this repeatedly, and it remains one of the most quietly arresting things the rovers have sent home. A blue sunset on a cold, silent, rust-colored world. The same physics, played on a different instrument, producing a different song. The universe uses the same rules everywhere, and yet everywhere looks different. The sunset on Mars is proof that the familiar can always become strange again, simply by changing the dust in the air. Your heartbeat can synchronize with the music you listen to, and your body does this without being asked. This phenomenon is called entrainment, and it is not unique to humans. Biological rhythms, from firefly flashing to neural oscillations, tend to synchronize with external periodic signals when those signals are strong and consistent enough. The human cardiovascular and nervous systems are particularly responsive to rhythmic auditory input. Studies have shown that listening to music with a strong, regular beat can cause measurable changes in heart rate, respiration, and even brainwave patterns, nudging them toward synchrony with the musical tempo. This is one reason why music feels physical, why a slow, quiet piece of music seems to slow time and soften the room, why a driving rhythm can make the body want to move without any conscious decision to do so. The body is not merely hearing the music, it is joining it, becoming, briefly, part of the same periodic pattern. The therapeutic implications of this are still being explored. Researchers have used rhythmic auditory stimulation in rehabilitation for patients with Parkinson's disease and stroke, helping to re-establish walking rhythms through the body's tendency to entrain to an external beat. Music therapy is a growing field, and the mechanisms are being slowly, carefully mapped. But underneath the science is something older. The body has always known that rhythm is not just heard, it is inhabited. You do not listen to a drum beat the way you read a sign. You are changed by it, subtly, at the level of pulse and breath, in ways that happen before thought. Even now, if you are listening to this voice, your breathing may be adjusting to its pace, slowing perhaps, settling. The body is always listening for something to follow into stillness. There is a cloud of alcohol drifting near the center of our galaxy, and it formed there naturally, without any help. The cloud is called Sagittarius B2, and it is one of the largest and most massive molecular clouds near the galactic center, a vast region of gas and dust spanning hundreds of light years, dense enough by interstellar standards to be rich in complex molecules. Among the many compounds detected within it is ethanol, the same molecule found in every fermented drink humans have ever made. Also present are other organic molecules, including some of the chemical precursors to amino acids. These molecules form through processes that occur naturally in the cold, radiation-bathed environment of interstellar space. Simple atoms and molecules on the surfaces of dust grains react slowly, over millions of years, building complexity one step at a time. The chemistry of space is not simple. Given time and the right conditions, space produces organic molecules with a quiet, unhurried productivity. The presence of complex organic molecules in interstellar clouds is one of the reasons scientists take seriously the idea that the chemical building blocks of life may be widespread in the universe. Not life itself, but the ingredients. The molecular precursors that, given a rocky planet, liquid water, and a few 100 million years, have been shown at least once to produce something that can look up and wonder where it came from. The galaxy's center is making organic chemistry tonight, in a cloud so vast it dwarfs our entire solar system, under conditions no laboratory can fully replicate. The universe is not waiting for life to arrive to begin preparing for it. In some quiet sense, the preparation has always been underway. The very first stars in the universe were made of almost nothing, and they burned with a strange, pure ferocity. The first stars formed when the universe was perhaps 100 to 200 million years old. Ancient by human reckoning, young by cosmic standards. The universe at that time contained only hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no iron, no silicon, none of the elements that make planets, or oceans, or living things, just the two simplest atoms in enormous clouds, slowly gathering under gravity. The stars that formed from this primordial material are called population 3 stars, and none of them are believed to survive today. They are thought to have been extraordinarily massive, perhaps hundreds of times the mass of our Sun, because the absence of heavier elements meant the gas clouds could not cool and fragment as efficiently as they do today, tending to collapse into fewer, larger objects rather than many smaller ones. More massive stars burn faster and hotter. Population 3 stars, if the models are correct, lived only a few million years before exploding as supernovae of extraordinary energy, seeding the young universe with the first heavy elements ever made: carbon, oxygen, iron. The elements that everything complex is built from, they came from these first stars, these enormous, solitary, brief burning things that lit the universe for the first time. No human eye will ever see a population 3 star. They are gone, but everything you are made of passed through one. The first fire made everything that the second fire could use, and the second fire made you. A tiny fraction of the static on an old analog television is the oldest light in the universe, arriving in your living room. The cosmic microwave background radiation, the afterglow of the hot early universe from approximately 380,000 years after the Big Bang, fills the entire sky in every direction, at every moment. It is not visible to the naked eye, because its wavelengths have been stretched by the expansion of the universe from the visible and infrared range all the way out to microwave frequencies. But it is detectable with the right instruments, and it is everywhere. Analog televisions, when tuned to a channel with no broadcast signal, display what is commonly called snow, a flickering, hissing pattern of random noise. That noise comes from many sources, including the electronics of the television itself, but a small fraction of it, somewhere between 1 and 10%, depending on the set and its orientation, comes from picking up ambient electromagnetic noise from the environment, and a tiny portion of that includes the cosmic microwave background. The background radiation was first accidentally detected in 1965 by Arno Penzias and Robert Wilson, working with a large horn antenna in New Jersey. They noticed a persistent noise in their instrument that they could not eliminate, regardless of what they did. They initially suspected pigeon droppings on the antenna. The noise persisted after cleaning. It turned out to be the echo of the Big Bang, arriving from every direction simultaneously, and the discovery earned them the Nobel Prize in Physics in 1978. The oldest light in the universe was confused, briefly, for pigeon droppings, and it has been arriving at your house every day of your life. The universe has always been closer than it appeared. Some mountains on Earth are still rising, grain by grain, and the ground has never once stopped moving beneath everything you have ever known. There is a particular kind of peace available in understanding that the Earth is not a finished thing. The Himalayas continue their slow upward press, pushed by the grinding of one continental plate against another, a collision that has been underway for 50 million years and shows no immediate sign of resolution. 5 centimeters per year, the width of a hand, accumulated over a year of days and seasons and ordinary human life, added invisibly to the tallest mountains on Earth. But the rising is only half the story. Simultaneously, wind and water and frost and the slow chemistry of weathering are working at those same peaks from above, dissolving, fracturing, and carrying material downward into rivers, and from rivers to the sea. The height of a mountain at any moment is not a fixed achievement. It is a negotiation, a balance between forces pushing up and forces wearing down, struck anew every day without announcement. The Appalachians tell the other side of this story. They are among the oldest mountain ranges on Earth, formed roughly 480 million years ago when ancient continents collided, and they were once perhaps as imposing as the Himalayas are today. Time and water have spent hundreds of millions of years in patient conversation with them, and what remains are gentle, forested ridges, rounded and quiet, rich with life, their original drama smoothed into something that feels almost restful. The Earth is always becoming, always in the middle of something. Right now, tonight, below the floor you rest on, below the foundations of everything built and everything grown, the slow work continues. Unannounced, unhurried, the planet doing what planets do, in the only time that has ever existed for it, which is all the time there is. A single bolt of lightning briefly burns hotter than the surface of the sun, and then the sky is quiet again. There is something the mind wants to resist about this. The sun is the standard of heat and light in all ordinary human experience. It is the thing that warms the world, that you cannot look at directly, that has governed the rhythm of every day of your life. And yet, in the channel of a lightning bolt, for a fraction of a second, the temperature reaches approximately 30,000 degrees Celsius, while the sun's surface burns at roughly 5,500 degrees. The lightning exists for perhaps a millisecond. The thunder that follows is the sound of air that has been heated so suddenly and so intensely that it expands faster than sound itself can carry the news, creating a shock wave. By the time the thunder reaches your ears, the lightning channel has already cooled. The extraordinary thing has already become ordinary air again. What strikes something quiet in the mind is not the heat itself, but the brevity. The universe is capable of producing, within the ordinary atmosphere of an ordinary planet, something briefly hotter than a star, and it does this routinely. On any given day, approximately 40 to 50 lightning bolts strike the Earth every second. While you slept last night, thousands of brief stellar temperatures were created and dissolved in storms over oceans and continents and forests. The extreme is not rare, it is simply fast. The universe keeps its most intense moments short and returns almost immediately to something that can be breathed and walked through and lived in. The storm passes, the sky clears, and the air, having briefly touched something solar, settles back into the ordinary business of carrying birdsong and the smell of rain. The universe may have no center, or every single point in it may be the center equally. This is not a riddle. It is one of the genuine, carefully considered conclusions of modern cosmology, and it follows directly from what we observe about the expansion of the universe. When astronomers measure the motion of distant galaxies, they find that every galaxy is moving away from every other galaxy, not because there was an explosion from a central point that flung things outward, but because space itself is expanding uniformly in all directions. Imagine a loaf of raisin bread rising in an oven. Every raisin moves away from every other raisin as the dough expands between them. No raisin is at the center. No raisin is at the edge. From the perspective of any raisin, all the others are receding, and the raisin itself appears to be the still point around which everything retreats. The universe behaves like that bread, in 3 dimensions, without a crust or a pan or an oven, and without any analogy that fully satisfies, because the universe is not inside anything. It is not expanding into empty space that was already there. Space itself is what is expanding, and there is no outside for it to expand into. The Big Bang was not an explosion at a point. It was an expansion of space everywhere, simultaneously. Every location in the universe is equally the place where the Big Bang happened, because the Big Bang happened at every location. The beginning was not somewhere else. It was here. It is always here. You are at the center of the universe. So is everything else. And somehow that makes the center feel less like a place of importance and more like a quality of belonging, something the universe gives to every point equally, without reservation, without hierarchy, without ever taking it back. Most of the universe is made of something we cannot see, and we know it only by the shape of what it bends. Dark matter does not emit light. It does not absorb light. It does not reflect it. It interacts with ordinary matter only through gravity, which means it is invisible to every telescope ever built, every detector ever designed for detecting electromagnetic radiation of any kind. We have never seen it directly. We may never see it directly, and yet we are quite certain it is there. The evidence comes from multiple independent lines of observation. Galaxies rotate in ways that cannot be explained by the visible matter they contain. The outer regions of galaxies rotate as fast as the inner regions, which should not happen if visible matter were all there is. Gravitational lensing, the bending of light from distant objects around massive foreground structures, shows more bending than the visible mass could produce. The large-scale structure of the cosmic web matches computer simulations only when dark matter is included. Dark matter is estimated to make up approximately 27% of the total energy content of the universe. Ordinary matter, everything you can see, touch, or detect with any instrument, accounts for only about 5%. The rest is dark energy, dark matter, and a universe that is, by a very large margin, beyond the reach of our senses. Scientists are genuinely uncertain what dark matter is made of. Several candidates have been proposed, including weakly interacting massive particles, axions, and primordial black holes, but none has yet been definitively detected. The search continues, in underground laboratories shielded from cosmic rays, in space-based observations, in particle colliders. The universe is mostly something we do not know, and the knowing is still underway. Hummingbirds live at the edge of what biology can sustain, and every night they step gently back from it. A hummingbird's heart beats somewhere between 1,000 and 1,260 times per minute during flight. Its wings beat 50 to 80 times per second, a blur invisible to the naked eye that produces the characteristic hum from which the bird takes its name. Its metabolism runs so hot, so fast, that it must consume approximately half its body weight in nectar every day, simply to sustain the rate of living it has chosen. This pace is extraordinary even by the standards of small, warm-blooded animals, and it is, straightforwardly, unsustainable through a cold night. A hummingbird that maintained its full metabolic rate through darkness would exhaust its energy reserves before morning and not wake up. So hummingbirds do something remarkable. At night, they enter a state called torpor, a controlled, reversible reduction in metabolic rate and body temperature that can take their internal temperature down to just a few degrees above the surrounding air, and their heart rate down to as low as 50 beats per minute, from over 1,000 beats per minute to 50, a reduction of more than 95%. In torpor, they are not quite asleep in the way you are drifting towards sleep now. They are something closer to paused. Their bodies have found a way to be less, temporarily, in order to continue being at all. And each morning, they warm themselves back up, shivering gently, the metabolic rate climbing back toward its brilliant, impossible peak, and resume the full velocity of their lives. The hummingbird knows something ancient about rest, that the willingness to become still, to let the fire drop low for a time, is not a retreat from life. It is what makes the life possible at all. The edge of the solar system is not a line, but a long, gradual letting go. There is no moment, no precise boundary, at which you could stand and say, Here the solar system ends and interstellar space begins. The transition is a fading, a slow relinquishment of influence, where the sun's power gradually yields to the broader environment of the galaxy. The heliosphere is the bubble of solar wind-charged particles streaming outward from the sun that defines the sun's sphere of influence. Its outer boundary, the heliopause, is where the solar wind slows to a stop against the interstellar medium, the thin gas and dust that fills the space between stars. Voyager 1 crossed this boundary in 2012 at a distance of roughly 121 astronomical units from the Sun, 121 times the distance between Earth and the Sun. But even beyond the heliopause, the Sun's gravitational influence extends much farther. The Oort cloud, a vast, spherical shell of icy bodies thought to surround the solar system at distances of perhaps 2,000 to 100,000 astronomical units, is gravitationally bound to the Sun. Comets that visit the inner solar system occasionally originate there, nudged inward by gravitational interactions over millions of years. The Oort cloud has never been directly observed. It is inferred from the trajectories of long-period comets. But if it exists as theorized, it extends nearly a quarter of the way to the nearest star. The solar system does not end. It softens. It loosens its hold gradually, reluctantly, across distances that take light weeks and then years to cross. The sun's reach is longer than any boundary drawn on a diagram. And in that long, gradual loosening, there is something that feels, quietly, like generosity. Your neurons fire in combinations the universe has never produced before and will never produce again. The human brain contains approximately 86 billion neurons. Each neuron forms connections, called synapses, with thousands of others. The number of possible configurations of neural activity across the entire brain, the number of distinct patterns of firing and resting that could, in principle, occur exceeds the number of atoms in the observable universe by many orders of magnitude. It is not a close comparison. This means that your experience of this particular moment, the precise configuration of memory and sensation and thought and feeling that constitutes what it is like to be you, right now, tonight, drifting toward sleep, is a pattern the universe has not produced before, in 13.8 billion years of existence. Not approximately unique, not statistically rare, genuinely, combinatorially singular. Neuroscientists are careful to distinguish between the number of possible states and the number of meaningful or distinct experiences. Not every possible neural configuration corresponds to a distinct conscious experience. The relationship between brain states and subjective experience, what philosophers call the hard problem of consciousness, remains one of the deepest unsolved questions in science. But the physical uniqueness is real and is not in dispute. The specific arrangement of connections in your brain, shaped by every experience you have ever had, every person you have ever known, every quiet evening and difficult day and unexpected moment of beauty, that arrangement has never existed before. It will not exist again. The universe, in 13.8 billion years, has gotten around to making you exactly once. And in this particular moment, whatever you are thinking and feeling and gently releasing as you settle toward sleep, that is something the cosmos is experiencing for the first and only time. That is not nothing. That is, in the quietest possible sense, everything. There are galaxies so distant that we will never know what they look like now, and that unknowing is its own kind of beauty. The universe has a horizon, and beyond it, information cannot reach us. But there is a subtler version of this limit that applies even to galaxies we can see. The most distant objects detectable by our best telescopes are receding from us faster than light, not because they are moving through space at that speed, but because the space between us and them is expanding so rapidly that the distance grows faster than light can cross it. This means that some galaxies we can currently observe are already, right now, beyond our cosmic horizon. Light they are emitting tonight will never reach us. The images we have of them are the last we will ever receive. We are looking at objects that have, in a meaningful sense, already said their final word to us, without either party knowing it was the last. The James Webb Space Telescope has observed galaxies from when the universe was only about 300 million years old. These galaxies have had more than 13 billion years to evolve since the light we see left them. They may have merged with others, transformed entirely, produced generations of stars we will never see. We hold only their portrait from infancy, ancient light that crossed the expanding universe to arrive at a mirror floating in space, and then traveled a little farther to become an image on a screen. There is something in this that feels not like loss, but like the natural shape of things. We are not meant to know everything. The universe is under no obligation to make itself fully legible. Some things are beautiful precisely because they are only partly seen, only briefly held, only known from a distance and a time that can never quite be closed. The galaxies at the edge of the observable universe are not hidden. They are simply far away, in a universe that is under no obligation to stop expanding so we can catch up. Beneath the ice of Europa, an ocean older than anything alive on Earth may be moving right now in the dark. Europa is one of Jupiter's 4 large moons, discovered by Galileo in 1610, and it is one of the most compelling places in the solar system for those who think carefully about where life might exist beyond Earth. Its surface is covered in ice, cracked and fractured into patterns that resemble the broken ice of Earth's polar seas. Below that ice, warmed not by sunlight, but by the tidal flexing of the moon's interior, caused by Jupiter's immense gravitational pull, liquid water is almost certainly present. The ocean beneath Europa's ice is estimated to contain more liquid water than all of Earth's oceans combined. It has likely been liquid for much of the solar system's history, billions of years of water. In the dark, under ice, in contact with a rocky seafloor that may host hydrothermal vents similar to those found on Earth's ocean floor. On Earth, hydrothermal vents support entire ecosystems that have never seen sunlight. Bacteria, tube worms, shrimp, crabs living communities powered entirely by the chemical energy of the Earth's interior. If similar vents exist on Europa's seafloor, the ingredients for life, as we understand it, may all be present in the dark, under the ice, right now. Scientists are genuinely uncertain whether life exists there. No mission has yet penetrated Europa's ice. A NASA mission called Europa Clipper launched in 2024 and is en route to conduct detailed flybys, studying the moon's surface and magnetic environment for signs of what lies beneath. An ocean in the dark, possibly older than any ocean on Earth, possibly not empty. The question is real. The answer is still traveling toward us. Every snowflake that has ever fallen has taken a path no other snowflake has taken, and the path is the shape. A snowflake begins as a microscopic dust particle in a cloud, around which water vapor condenses and freezes into a tiny ice crystal. As it falls, it passes through regions of slightly different temperature and humidity, varying by fractions of a degree, varying by tiny differences in the concentration of water vapor, and at each moment, the crystal grows in response to those conditions. Warmer and more humid air produces broader, flatter branches. Colder and drier air produces simpler, more columnar forms. The path a snowflake takes through a cloud is unique. No two ice crystals follow exactly the same trajectory through exactly the same sequence of microscopic atmospheric conditions. And because the shape of a snowflake is the physical record of every condition it encountered on the way down, no two snowflakes are exactly alike. This is not merely tradition or poetic convention. Snowflake researcher Kenneth Liebrecht at Caltech has spent decades studying ice crystal growth, and while he notes that very simple crystals, tiny, early-stage ones, can be nearly identical, the complex, branched, fully developed snowflakes familiar from photographs are, in all meaningful senses, unique. The number of possible arrangements of water molecules in a fully grown snowflake vastly exceeds the number of atoms in the observable universe. Each winter, billions of snowflakes fall on every snowy landscape. Each one is the record of a small journey through a particular patch of sky, shaped by conditions that existed only once, at that moment, in that place. The snow on the ground is a library of individual journeys, none of them written down, all of them real. The human eye can detect a single photon of light, and this makes you more sensitive to the universe than you may have known. A photon is the smallest possible unit of light. It is a quantum of electromagnetic energy, indivisible, the minimum amount by which light can exist. And under the right conditions, in a very dark room, after the eye has had time to adapt, the human retina can register the arrival of a single one. This was demonstrated experimentally in a 2016 study in which participants were asked to report perceiving a flash of light when individual photons were directed at their eyes. The results showed that humans can, on rare occasions, consciously perceive a single photon, though the experience is described as extraordinarily faint and uncertain, less like seeing a light, and more like having the vague impression that something may have just happened. The rod cells in the human retina, the photoreceptors responsible for low-light vision, are extraordinarily sensitive. A single photon, absorbed by a rod cell, triggers a cascade of molecular events that amplifies the signal enormously before it reaches the brain. The eye is, in a very precise sense, a single photon detector. This means that on a clear, dark night, looking up at the sky, you are detecting individual photons that have traveled for years, centuries, millennia from distant stars. The light from Andromeda that reaches your eye arrives as a stream of photons that have been traveling for 2.5 million years. Some of those photons land on your retina and trigger a response. You see the galaxy, faint and soft, because ancient light is arriving in your eye one particle at a time. You are not just looking at the universe, you are catching it, photon by photon, in the most delicate net biology ever made. Coral reefs grow so slowly that a reef you could swim across in minutes may have been building itself for thousands of years. Coral reefs are among the oldest living structures on Earth. The Great Barrier Reef, the largest reef system in the world, stretching over 2,300 kilometers along the northeastern coast of Australia, began forming in its current configuration approximately 20,000 years ago, during the last ice age, when sea levels were lower and the continental shelf lay exposed. The living reef we know today, built atop ancient foundations, has been growing for somewhere between 6,000 and 8,000 years. Individual coral polyps, the tiny animals that build the reef, are soft-bodied creatures that secrete calcium carbonate skeletons. These skeletons accumulate, generation upon generation, into the hard substrate of the reef. Depending on the species, coral grows between 0.3 and 10 centimeters per year. The massive, boulder-like brain corals grow at the slower end of that range. A colony the size of a large armchair may be several hundred years old. Coral reefs occupy less than 1% of the ocean floor, and yet they support approximately 25% of all marine species. They are, by the measure of biodiversity per unit area, among the most productive ecosystems on Earth. Assembled slowly, over timescales that dwarf human history, by animals smaller than a fingernail, they have created habitats of staggering complexity and beauty. The patience of the reef is almost incomprehensible from the inside of a human life. And yet, here they are, built grain by grain and polyp by polyp, in the slow, warm, ancient water, over thousands of years of quiet effort that no individual coral ever knew it was part of. Something very large can be built by something very small, over a very long time, without any plan. The reef is proof. There are worlds drifting between the stars with no sun to warm them, and they travel in a darkness older than our solar system. Rogue planets, sometimes called free-floating planets or interstellar planets, are planetary mass objects that travel through interstellar space unbound to any star. They were not always alone. Most are thought to have formed in planetary systems and been ejected through gravitational interactions with other planets or with passing stars early in those systems' histories. Some may have formed directly from collapsing gas clouds, in the way that stars form, but without accumulating enough mass to ignite fusion. The first confirmed detections of rogue planets came through gravitational microlensing, a technique in which a massive object passing between Earth and a distant star briefly bends and amplifies the star's light, revealing the presence of something massive that is otherwise invisible. Statistical analyses of microlensing surveys suggest that rogue planets may be extraordinarily common, possibly more numerous than stars in the Milky Way. These worlds travel in complete darkness. No sunrise, no seasons, no warming light from any direction. Their surfaces, if rocky, are frozen. And yet, some planetary scientists have pointed out that worlds large enough, or sufficiently rich in radioactive elements, might maintain liquid water in subsurface oceans warmed by internal heat alone, regardless of the absence of a star. Life, in principle, might not need a sun. A rogue planet is not a tragedy. It is a different kind of world, following a different kind of path, in the dark between stars, belonging to no system and no sun, moving through the galaxy on its own slow arc, carrying whatever it carries in its interior through a darkness that has never been interrupted by dawn. Not lost, simply traveling alone, in the ancient dark, the way some things do. Sound cannot travel through space, and so the most dramatic events in the universe happen in absolute silence. Sound is a pressure wave. It requires a medium, a substance through which alternating compressions and rarefactions can propagate. In air, sound travels at roughly 343 meters per second. In water, faster. In steel, faster still. But in the near vacuum of interstellar space, where the density of matter is so low that you might find only a handful of atoms per cubic centimeter, there is not enough medium for ordinary sound to propagate in any meaningful way. This means that a supernova, the explosive death of a massive star, a detonation so energetic it briefly outshines the entire galaxy containing it, happens in silence. The shock wave it sends through surrounding gas is real, and the gas carries something like a pressure wave, but at densities and timescales so different from anything we would recognize as sound that the experience, if you could somehow be nearby without being destroyed, would be purely visual. A vast, expanding shell of gas and light and radiation in absolute quiet. Black holes consuming matter, neutron stars colliding and merging, galaxies distorting each other across millions of light-years of gravitational interaction. All of it, all the most powerful and dramatic physics the universe enacts, unfolds in complete silence. There is something about this that the mind finds both eerie and deeply peaceful. The universe's largest events have no sound. They are light shows, gravity shows, radiation events, playing out in a silence so total it has no earthly analog. The closest you might come is the silence at the very bottom of a very deep cave, where no sound from the surface reaches, multiplied by everything. The universe is quieter than you can imagine, and in that quiet, everything is always happening. Your cells contain ancient bacteria that chose, billions of years ago, to stay. Inside almost every cell in your body, tucked within the cytoplasm like small, dedicated tenants, are structures called mitochondria. They generate the energy your cells run on, converting oxygen and nutrients into a molecule called ATP, the universal energy currency of life. Without them, complex life as we know it would not exist, and they were not always part of us. Approximately 1.5 to 2 billion years ago, in the ancient ocean of an early Earth, an event occurred that changed the direction of life entirely. A larger cell engulfed a smaller bacterium. This had happened countless times before, usually ending in digestion, but this time, something different happened. The bacterium was not destroyed. It survived inside its host, and the two discovered that they were more useful to each other than either was alone. The bacterium provided efficient energy production. The host provided protection and resources. Over generations, over millions of years, the two became one. The bacterium gradually transferred much of its DNA to the host cell's nucleus, becoming dependent on the host for many functions it once performed independently. What remained became the mitochondrion. It still carries its own small loop of DNA, separate from the rest of your genome, a remnant of its independent past. It still divides on its own schedule, inside your cells, like the bacterium it once was. You are, in the most precise biological sense, a collaboration. Not a single organism, but a merger, still ongoing, between lineages that found each other in an ancient sea and decided, without deciding anything, to stay together. Every breath you take is powered by that ancient partnership. Every thought, every heartbeat, every quiet moment of rest. An alliance struck 2 billion years ago, still honored, still holding, in every cell of you right now. There is a star that appears nearly as old as the universe itself, and it is close enough to see with a small telescope. HD 140283 sits in the constellation Libra, approximately 190 light-years from Earth. By stellar standards, that is practically next door. On a clear night, with a modest telescope, you could point it at the right patch of sky and collect light from a star that has been burning since the universe was in its earliest period. Light that left a star born before the Milky Way had assembled itself into anything like its current form. The star is what astronomers call metal-poor, meaning it contains very small amounts of elements heavier than hydrogen and helium. This is a fingerprint of extreme age. The first stars formed from the primordial hydrogen and helium of the Big Bang, before any stellar explosions had seeded the universe with heavier elements. Stars that formed very early carry that signature of simplicity, that near absence of complexity, in their spectra. Measuring the age of a star this old requires careful modeling of stellar evolution, how a star of a given mass and composition changes over time, and the uncertainties are real and honestly acknowledged by the researchers involved. The best current estimates place HD 140283 at approximately 13.6 to 14.5 billion years old, with error bars that make it consistent with the age of the universe rather than older than it. What remains after the numbers is this: a star, visible from your backyard, that has been burning since before Earth existed, before the Sun existed, before any planet in this solar system took shape. It has watched the Milky Way form around it. It has outlasted generations of stars that burned bright and brief while it burned quietly on. It is still there, still burning, patient in a way that makes patience feel like an entirely different kind of thing. Ocean tides are the moon and the Earth in a slow, continuous conversation, and every tide you have ever watched was part of that exchange. The moon's gravity pulls on everything on Earth, but it pulls more strongly on the side of Earth closest to it, and less strongly on the far side. This difference in gravitational pull, called a tidal force, stretches the Earth slightly along the axis pointing toward the moon, raising two bulges of water on opposite sides of the planet, one facing the moon and one facing away. As the Earth rotates beneath these bulges, a point on the surface passes through high tide roughly twice a day. The exchange is not one-directional. The tidal bulge on Earth's surface is carried slightly ahead of the moon's position by Earth's faster rotation. This misalignment means the bulge exerts a small forward gravitational tug on the moon continuously, adding a tiny amount of energy to the moon's orbit. That energy slowly pushes the moon farther from Earth, about 3.8 centimeters per year, as mentioned earlier in our journey tonight. And in return, Earth's rotation is gradually slowing by about 1.4 milliseconds per century. The oceans are the most visible part of this conversation, but the solid Earth also flexes. The ground beneath your feet rises and falls by several centimeters twice a day in response to tidal forces, a movement called Earth tides. that is too slow and too distributed to feel, but is measurable with precise instruments. Every tide that has ever come in, every wave that has ever reached a little farther up a beach in the evening than it did that morning, every coastal rhythm that fishermen and sailors and shorebirds have oriented their lives around, is the moon speaking to the ocean, and the ocean, slowly, is writing the moon's path in return. The conversation has been underway for 4.5 billion years. It is still going tonight. A single breath of air connects you to every human who has ever lived. The atmosphere contains an enormous number of molecules. A single breath, approximately half a liter of air, contains roughly 10 to the 22nd power molecules of nitrogen and oxygen and argon and other gases. That is 10 billion trillion molecules. In a single breath, the atmosphere is also very well mixed. Air circulates globally over timescales of years, meaning that molecules from any given location spread over a few years throughout the entire atmospheric volume. This mixing has been happening for billions of years, and the atmosphere has been the atmosphere, in something like its current composition, for hundreds of millions of years. The implications, when worked through carefully, are quietly extraordinary. A calculation first popularized by physicist Cesare Emiliani and repeated in various forms since suggests that any given breath contains molecules that have, with very high probability, been breathed by every human being who ever lived. Julius Caesar, the first person to cross the Bering Land Bridge, your great-great-grandmother. Every person who has ever breathed on this planet has exhaled molecules that have, over time, distributed themselves throughout the atmosphere, and some of them are in the air you are breathing right now. The same calculation applies to many other historical figures, and to many other breaths and many other moments. You are not breathing air. You are breathing the accumulated exhalations of everyone who has ever been alive on this planet, gently mixed by wind and time into a shared atmosphere that belongs to everyone and no one, that carries the breath of the long dead to the lungs of those still living, quietly and without ceremony, with every breath, all night long. Magnetars are the most intensely magnetic objects known, and one nearby could erase every hard drive on Earth from the distance of the moon. A magnetar is a type of neutron star with a magnetic field of extraordinary strength. Neutron stars already have magnetic fields far beyond anything on Earth, but magnetars take this further by orders of magnitude. The magnetic field of a magnetar is estimated at roughly 10 to the power of 15 Gauss. For comparison, a typical refrigerator magnet produces about 100 Gauss. Earth's magnetic field is roughly half a Gauss. The magnetic field of a magnetar is so strong that it affects the structure of atoms themselves, distorting the electron clouds around atomic nuclei into elongated shapes rather than the roughly spherical forms they take in ordinary conditions. Matter, in the presence of a magnetar's surface field, behaves in ways that have no earthly analog. If a magnetar were located where our moon is approximately 385,000 kilometers away, its magnetic field would be strong enough to destroy the iron-containing molecules in your body's cells and erase every magnetic storage device on the planet. Every hard drive, every credit card, magnetic strip, every magnetically stored piece of information, gone. The nearest known magnetar is approximately 9,000 light-years away. We are safe, in a very absolute sense. But the existence of magnetars is a reminder that the universe contains objects operating so far outside the range of ordinary experience that the words we use to describe them, strong, hot, dense, fast, become almost meaningless. Our language was built for a world of moderate things. The universe is under no obligation to remain moderate. And yet here we are, on a world of moderate things, in a moderate corner of a moderate galaxy, where the most magnetic thing most people will ever encounter is holding a note to a refrigerator. That is not a complaint. That is, in the most genuine sense, exactly where you want to be. Seasons on Uranus last 21 years, and the planet experiences them lying entirely on its side. Uranus is tilted, where Earth's axis tilts at approximately 23.5 degrees relative to its orbital plane, giving us the gentle progression of seasons we know. With the northern hemisphere leaning toward the Sun in June and away in December, Uranus is tilted at approximately 98 degrees. It is, in effect, rolling around the Sun on its side, with its poles pointing roughly toward and away from the Sun, rather than perpendicular to the orbital plane. The result is a seasonal pattern unlike anything in the inner solar system. During Uranus's summer, one pole points almost directly at the Sun and receives continuous sunlight for approximately 21 years, while the other pole sits in continuous darkness. Then, as Uranus completes its 4-year orbit, the situation reverses. The dark hemisphere slowly tilts toward the Sun, and what was summer becomes a 1-year winter, and the other pole begins its long, dark, cold night. Scientists are not entirely certain how Uranus came to be tilted this way. The leading hypothesis involves a large impact early in the solar system's history, a collision with an Earth-sized object that knocked the planet onto its side. But the details of exactly how such an impact could have produced the current tilt, and why Uranus's moons are also tilted with it, are still being worked out. What remains is the image of a planet rolling slowly around the Sun, its poles taking turns in the light, each season lasting longer than most human lives. A world keeping its own time, in its own orientation, indifferent to the conventions of the solar system it shares with us, tilted, patient, distinctly itself. Every star you can see tonight is a sun, and around many of them, worlds are turning right now in the dark. For most of human history, the question of whether other stars had planets was unanswerable. Not hypothetically unanswerable, genuinely, technically beyond the reach of available instruments. The planets are small and dark, and close to their stars, drowned in starlight, invisible at interstellar distances with anything early astronomy could build. The first confirmed detection of planets orbiting a sun-like star came in 1995. Since then, the pace has accelerated enormously. The Kepler Space Telescope, launched in 2009 and operating until 2018, discovered thousands of exoplanets by watching for the tiny, regular dimming of a star's light as a planet passed in front of it. The TESS mission, its successor, has continued that work. As of recent counts, more than 5,500 exoplanets have been confirmed, with thousands more candidates awaiting confirmation. The statistical results from these surveys have been striking. Virtually every star appears to have at least one planet. The Milky Way likely contains hundreds of billions of planets. Some of these are rocky, roughly Earth-sized worlds, orbiting in the zone where liquid water could exist on their surfaces. Dozens of such worlds have already been identified. Whether any of them hosts life, we do not know. The question is not settled. The instruments to answer it directly are only now being developed, and the answers, if they come, may take decades. But tonight, above you, every point of light in the sky is almost certainly a sun with worlds. Right now, on some of those worlds, something may be looking up at a sky that contains our sun, a faint and ordinary star among billions, and perhaps wondering, quietly, the same things you wonder. You are not alone in the universe. At least, the universe has given that question more room to breathe than it ever had before. The number of stars in the observable universe is roughly equal to the number of grains of sand on every beach and desert on Earth, and neither number means anything until you try to hold it. Estimates of the total number of stars in the observable universe sit at approximately 1 to 2 times 10 to the power of 23. That is a number so large that the mind cannot actually picture it, only gesture toward it. The same is true of grains of sand. Researchers at the University of Hawaii estimated the number of grains of sand on Earth's beaches at approximately 7.5 times 10 to the 18th power, and when desert sand is included, the estimate climbs toward the same range as the stellar count. The comparison is not meant to make either number feel smaller. It is meant to give the vastness of the universe a texture, a material analog, something your hand has touched. You have walked on beaches. You have felt sand between your fingers, watched it fall from a closed fist, noticed how many grains exist in a single footprint, in a single handful, in a single dune, and then you are asked to imagine that many stars, each one a sun, each one burning with fusion, maintaining temperature and pressure and light across a lifespan of millions or billions of years, each one almost certainly surrounded by planets, each one separated from its neighbors by distances so vast that the light between them takes years to cross. The sand comparison does not make the universe smaller. It makes it larger in a different way, a way the body can almost feel rather than merely calculate. You have held sand. You know what a handful is, and the universe contains a star for every grain of everything like that, spread across every shore you have ever stood on. The mind cannot hold it. It was never meant to. It can only open, gently, in the direction of it. A photon of light may spend 100,000 years inside the sun before it escapes, and then cross the solar system in minutes. This fact carries a particular kind of poetry when held alongside itself. The sun is not a transparent object. Its interior is so dense, so full of charged particles, that light cannot travel in a straight line for more than a tiny fraction of a millimeter before being absorbed and re-emitted in a random direction. The photon essentially forgets where it was going. It wanders. This wandering, this random walk through the solar interior, takes an extraordinarily long time to carry energy from the core, where it is produced, to the surface, where it can finally escape. The commonly cited estimate ranges from 10,000 to 100,000 years, with some models suggesting even longer for photons originating deepest in the core. And then the surface is reached. The photon enters what astronomers call the photosphere, the layer thin enough that it can finally travel freely. And in 8 minutes and 20 seconds, it crosses the 150 million kilometers between the Sun and Earth. The journey that took 100,000 years inside the star takes 8 minutes in the open. There is a quality of recognition in this, if you sit with it long enough. Some things take an extraordinarily long time to reach the surface. Some forms of understanding, some realizations, some feelings that have been working their way through layers of interior density for years, suddenly emerge and cross the remaining distance in almost no time at all. Not all journeys move at the same speed throughout. The Sun has known this longer than the Earth has existed. It has been patiently releasing its ancient interior light, one freed photon at a time, for 4.5 billion years. None of it wasted. All of it, eventually, arriving. Fireflies in certain forests synchronize their flashing until an entire hillside pulses together, and no one is conducting. In the forests of the Great Smoky Mountains in Tennessee, and in certain forests in Southeast Asia, particularly in parts of Malaysia and Thailand, large populations of fireflies synchronize their bioluminescent flashes into coordinated, rhythmic pulses that sweep through entire hillsides and riverbanks. At the peak of the synchronization, thousands of lights flash together, go dark together, and flash again, in waves of light that have no director, no leader, no central coordination of any kind. The mechanism is biological entrainment of the same general kind that allows your heartbeat to synchronize with music, though in the fireflies it is visual rather than auditory. Each firefly has an internal oscillator, a biological rhythm governing its flash rate. When a firefly perceives flashes from others nearby, it adjusts its own rhythm slightly toward theirs. Over time, through countless local adjustments, the whole population converges on a shared rhythm. This is called emergent synchronization, and it appears across many complex systems, the firing of neurons in the brain, the rhythm of applause in a concert hall that spontaneously organizes into a clap, the oscillations of coupled pendulums sharing a wall. The synchronization is not planned. It arises from simple local rules applied across many individuals and produces something that looks, from a distance, like intention. The Smokies Fireflies synchronization event, which occurs for a few weeks each summer, draws visitors from across the country who stand in the dark among the trees and watch the hillside pulse. No one speaks much. The lights do not need commentary. They are their own complete thing, a conversation the fireflies are having with each other, in light, in the warm dark, that has been happening in these forests for far longer than anyone has been there to witness it. There is a planet where it may rain glass, sideways, driven by winds of extraordinary speed in eternal darkness. The planet is HD 189733b, a gas giant roughly the size of Jupiter orbiting very close to its host star, located approximately 64 light-years from Earth. It is tidally locked, meaning one side of the planet always faces the star, in permanent scorching noon, while the other side faces permanently away, in permanent dark. The temperature difference between these two hemispheres drives winds of extraordinary violence, estimated at speeds of up to 8,700 kilometers per hour, more than 20 times the speed of sound on Earth. The planet's atmosphere contains silicate particles, tiny grains of the material that makes up glass and much of Earth's crust, suspended in the upper atmosphere. The extreme temperatures on the day side are thought to vaporize these silicates, which are then carried by the ferocious winds to the cooler night side, where they condense and may precipitate as tiny solid particles, raining sideways through the dark at wind speeds that would strip any surface they encountered. Scientists are careful to note that the exact nature of the precipitation is modeled rather than directly observed. What is confirmed is the presence of silicates in the atmosphere, the extreme temperature differential, and the extraordinary wind speeds. The glass rain is a reasonable inference from those conditions, but the details remain subject to refinement as better observations become possible. HD 189733b is also one of the most intensely blue planets known, not from oceans or sky, but from the scattering properties of those silicate particles in its upper atmosphere. A deep, vivid blue, on a world of searing heat and violent wind and sideways glass, orbiting so close to its star that a year there lasts only 2.2 Earth days. The universe makes beautiful things in places where beauty serves no purpose, for no audience, continuously. The Milky Way takes 225 million years to complete one full rotation, and this unit of time has a name. A cosmic year, sometimes called a galactic year, is the time it takes for the solar system to complete one orbit around the center of the Milky Way. The current best estimate is approximately 225 to 250 million years. In the 4.5 billion year history of Earth, our planet has completed roughly 18 to 20 of these galactic orbits. We are, in galactic terms, a world that has gone around the block about 20 times. One cosmic year ago, in the Triassic period, the first dinosaurs were beginning to appear on Earth. The continents were arranged differently. The Atlantic Ocean did not yet exist. The atmosphere had a different composition. Everything that has happened in the entire history of the dinosaurs, their rise, their extraordinary diversification, and their extinction, and then everything that has happened since, all of human prehistory and history, all of civilization, all of recorded time, has occurred in less than one cosmic year. 2 cosmic years ago, the Permian-Triassic extinction event, the largest mass extinction in Earth's history, was underway, eliminating perhaps 96% of all marine species and 70% of terrestrial vertebrate species. 4 cosmic years ago, complex multicellular animal life was only just beginning to diversify in the Cambrian explosion. The Milky Way does not know any of this. It rotates in its own time, carrying the solar system with it at a speed of approximately 828,000 kilometers per hour relative to the galactic center, smoothly, continuously, in a vast slow arc that will take another 225 million years to complete. We are, right now, at some particular point in that arc, moving, always moving, carried by the galaxy itself, through the night, through all the nights, at a speed that would cross a continent in seconds and that you will never once feel. In drought, trees share water with their neighbors through the underground, and the forest decides, quietly, to survive together. The mycorrhizal networks that connect forest trees are not merely channels for nutrients under ordinary conditions. Research by forest ecologist Suzanne Simard and others has documented that during periods of water stress, mature trees increase the flow of carbon and water to neighboring trees, including trees of different species, through the fungal networks in the soil. The mechanism involves the fungi that form symbiotic relationships with tree roots, threading into them and extending far beyond their reach into the surrounding soil. These fungi exchange nutrients and water for carbon from the tree, but the network they form also connects different trees, creating pathways through which resources can move. During drought, when smaller or younger trees are most vulnerable, measurements have shown elevated transfer of resources from larger, more established trees that have deeper root access to water. Scientists are careful about how much intentionality to attribute to this. Trees do not decide anything in the way that word implies for humans. What is happening is a complex interplay of biochemical signals and gradient-driven flows, resources moving along concentration gradients the way water flows downhill. But the outcome, whatever its mechanism, is that a forest under stress distributes resources in ways that support its weaker members. The forest, as a system, tends toward its own continuation, not because any tree planned it, but because the network connecting them has properties that the individual trees do not have alone. Together, they are more resilient than apart. The drought presses down, and the forest, underground, in the dark, in the slow chemistry of root and fungus, leans towards survival. Every system that learns to share its resources discovers that it can endure more than any of its parts could alone. In the deep future, all of Earth's continents will likely gather again into one, the way they have done before, without hurry, without anyone left to name it. The continents move, they always have, driven by convection currents in the mantle far below, the slow churning of rock so hot it flows like an extraordinarily viscous fluid over millions of years. The surface plates of the Earth ride on this slow current, colliding, separating, sliding past each other, in a process called plate tectonics that has been operating for at least 3 billion years. Approximately 335 million years ago, all of Earth's landmasses were gathered into a single supercontinent called Pangaea, surrounded by a single global ocean called Panthalassa. Before Pangaea, there were earlier supercontinents, Rodinia, Nuna, each forming and breaking apart in cycles that have operated throughout most of Earth's history. The current arrangement of continents, with the Atlantic widening and the Pacific slowly shrinking, is simply the latest configuration in this very long series of gatherings and dispersals. The models suggest that in approximately 250 to 300 million years, the current continents will converge again. The Atlantic will close. Asia and the Americas will collide. A new supercontinent, sometimes called Pangaea Proxima or Amasia in different models, will form in what is now the Arctic Ocean region, or possibly centered differently depending on which model you consult. The details are uncertain. The general direction is not. Whatever exists on Earth by then, if anything does, will not know the world we know. The oceans will have different shapes. The mountains will be different mountains, raised by collisions we cannot yet predict, in places we have not yet named. The Earth will continue its slow rearrangement, continent by continent, ocean by ocean, without urgency, without memory of what it was before, building the next version of itself in the only time it has ever known, which is all the time there is. You share more than half of your DNA with a banana, and the library of life turns out to be very old and very shared. This is one of those facts that sounds like a joke until you sit with it long enough for it to become something else entirely. The genetic code, the system by which sequences of DNA are translated into proteins, is essentially universal across all life on Earth. The same codons, the same translation machinery, the same fundamental molecular language, appears in bacteria, in fungi, in plants, in animals, in you. This universality is one of the strongest pieces of evidence that all life on Earth descends from a common ancestor, a single lineage that established this molecular grammar billions of years ago and passed it down, unbroken, to everything alive today. The 60% figure for shared DNA between humans and bananas refers specifically to genes involved in basic cellular functions, the machinery of metabolism, cell division, energy production, DNA replication. These processes are so fundamental, so deeply conserved by evolution, that the genes governing them have remained recognizable across more than 1 billion years of separate evolutionary history. The differences, of course, are real and significant. The remaining 40% and the regulatory sequences that control when and how genes are expressed account for the vast difference between a banana and a person. But the shared 60% is not trivial. It is the deep foundation, the ancient grammar beneath everything life does. You are not a banana, but you and the banana share an ancestor so distant, so ancient, that it predates everything with eyes or legs or any complexity we would recognize. And in the core of your cells, in the molecules that keep you alive tonight, that ancient kinship is still legible, still operating, still carrying the original instructions forward into the future in every living thing at once. The James Webb Space Telescope captures light that has been traveling toward us longer than the Earth has existed, and it does so from a point 1 million miles from home. The James Webb Space Telescope orbits the Sun at a location called the second Lagrange point, approximately 1.5 million kilometers from Earth, in the direction away from the Sun. At this point, the gravitational influences of the Earth and Sun combine in a way that allows the telescope to maintain a stable orbit while always keeping the Earth and Sun on the same side, behind its large sunshield. The sunshield, roughly the size of a tennis court, keeps the telescope's instruments at temperatures near absolute zero, cold enough to detect the faint infrared light of the most distant galaxies. The Webb telescope observes primarily in infrared wavelengths, light that is invisible to the human eye, but carries information that optical light cannot. The most ancient galaxies have had their light stretched by the expansion of the universe from visible wavelengths into infrared during its billions of years of travel. Only an infrared telescope can see them clearly. Since its first science images in July 2022, Webb has observed galaxies from when the universe was only a few 100 million years old. It has found galaxies that were larger and more mature than models predicted they should be at that age, a discovery that has sent cosmologists back to their models with genuine puzzlement and excitement. The early universe, it turns out, was building things faster than we thought. 1 million miles from Earth, in the cold, dark, pointed at the oldest light in the universe, Webb is answering questions that humanity has held for as long as it has looked up. And in answering them, it is producing new questions, deeper ones, in the way that real answers always do. The universe rewards the looking. It always has something further to show. Some rivers run silently along the ocean floor, invisible and ancient, carrying cold water in slow currents that shape the climate of the world above. The ocean is not a uniform body of water. It is stratified, layered by temperature and salinity into distinct water masses that move in patterns collectively called thermohaline circulation, or the global ocean conveyor belt. At the surface, wind-driven currents move water horizontally across ocean basins. But deep below, driven by differences in density rather than wind, cold and salty water sinks and flows along the seafloor in slow, deep rivers that take hundreds to thousands of years to complete their journeys. In certain locations, particularly in the North Atlantic and around Antarctica, surface water becomes dense enough, cooled by cold air, made saltier by evaporation or sea ice formation, to sink to the deep ocean. This sinking drives a slow circulation that carries cold water along the bottom of the Atlantic, around the tip of Africa, into the Indian and Pacific Oceans, where it slowly warms and rises again, eventually returning to the surface and flowing back toward the poles. This circulation takes approximately 1,000 years to complete one full cycle. The deep water flowing along the Atlantic seafloor tonight may have last been at the surface during the medieval period, before Columbus crossed the ocean above it. The deep ocean currents redistribute heat around the planet, moderating climates, carrying nutrients from the deep to the surface, where they feed the base of the marine food web, and playing a role in regulating the concentration of carbon dioxide in the atmosphere over long timescales. The weather above the ocean is partly determined by water that sank 1,000 years ago. The world is deeper and slower and more interconnected than the surface suggests. The patient currents below are always shaping what happens above, quietly, in the dark, over centuries. Certain stars pulse in brightness with such regularity that they became the rulers by which the universe was measured. Cepheid variable stars are a class of stars that expand and contract in a regular cycle, brightening and dimming with a period that can range from a few days to several months. The pulsations are driven by a layer of ionized helium in the star's outer atmosphere that alternately absorbs and releases radiation, acting like a valve that makes the star breathe in and out in a slow, steady rhythm. In 1908, astronomer Henrietta Leavitt, working at the Harvard College Observatory, was studying photographs of stars in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. She noticed that the brighter Cepheid variables in the cloud had longer periods. Since all the stars in the Small Magellanic Cloud were approximately the same distance from Earth, differences in apparent brightness reflected real differences in luminosity. Leavitt had discovered a relationship between the period of pulsation and the intrinsic brightness of the star. This relationship became one of the most powerful tools in the history of astronomy. By measuring how long a Cepheid takes to complete one pulse, you can calculate how intrinsically bright it is. By comparing that intrinsic brightness to how bright it appears from Earth, you can calculate its distance. Cepheids became, in effect, standard candles, known brightnesses held up at unknown distances to measure how far the darkness extends. Using Cepheids, Edwin Hubble demonstrated in the 1920s that the Andromeda Nebula was far beyond the Milky Way, a galaxy in its own right, and that the universe was vastly larger than had been imagined. He later used them to discover that galaxies were receding from us, leading to the understanding that the universe was expanding. A star that breathes measured the size of everything, and a woman who noticed the pattern of its breath changed our understanding of where we are. The smell of rain on dry Earth has a name, and it comes partly from ancient bacteria releasing something into the air. Petrichor is the word, coined in 1964 by Australian researchers Isabel Joy Baer and Richard Thomas, who identified the compounds responsible for the distinctive smell of rain on dry ground. The name comes from the Greek words for stone and the fluid that flows in the veins of the gods, which is perhaps the most poetic etymology in all of atmospheric chemistry. The smell has two main sources. The first is geosmin, a compound produced by soil bacteria called actinomycetes as part of their normal metabolism. Geosmin accumulates in dry soil during rainless periods. When rain falls, it disturbs the soil and releases geosmin into the air as tiny aerosol droplets. Human noses are extraordinarily sensitive to geosmin. We can detect it at concentrations of a few parts per trillion, which may reflect an evolutionary history in which the smell of rain served as a signal that water and food were nearby. The second source is plant oils that accumulate in dry soil and rock during drought and are released by rain. These oils contribute to the earthy, complex quality of the full petrichor scent. Geosmin is also what gives beets their earthy flavor and what you sometimes smell in water from certain sources. It is the smell of living soil, of bacteria going about their ancient business in the ground beneath the grass. Every time rain falls on dry earth and you breathe in that particular smell, You are smelling the exhalations of bacteria that have lived in the soil since before the age of the dinosaurs. Ancient life, announcing rain, in a language the human nose learned to love so long ago that no one alive remembers why. The rain smells like home because something very old has been making it smell that way for a very long time. Enormous cosmic voids shape the universe the way silence shapes music, and without them, everything beautiful would collapse into sameness. The large-scale structure of the universe, the cosmic web of filaments, clusters, and nodes where galaxies congregate, owes its existence as much to what is not there as to what is. Cosmic voids, those vast regions of relative emptiness that occupy most of the universe's volume, are not merely absences. They are active participants in the gravitational dynamics that shape the web. Matter does not distribute itself uniformly through space. Tiny fluctuations in the density of the early universe, imprinted in the first moments after the Big Bang and visible in the patterns of the cosmic microwave background, grew over billions of years as gravity amplified them. Regions slightly denser than average attracted more matter. Regions slightly less dense lost matter to their denser neighbors. Over time, the dense regions became filaments and clusters, and the less dense regions became voids, growing emptier as matter drained away toward the surrounding structure. Voids are not static, they expand. As the matter inside them falls outward toward the surrounding filaments, the void grows, slowly pushing the walls of the cosmic web outward and contributing to the overall expansion of the large-scale structure. In the most detailed maps of the universe, voids and filaments alternate in a pattern that has been called the cosmic foam, a three-dimensional structure of bubbles and walls that extends across hundreds of millions of light-years. The Berthes void, which we visited early in our journey tonight, is one of the largest known voids, a region of relative emptiness so vast it challenges our models. But smaller voids are everywhere. The spaces between the threads of the web, the silence between the notes. Music needs silence to be music. The universe needs emptiness to have structure. The nothing is not nothing. It is the shape that holds everything else in place. Your skeleton is not the fixed, permanent thing it feels like. It is quietly rebuilding itself. Your whole life long, bone feels permanent. It is the hardest tissue in the body, the framework that outlasts everything else, the part of us most likely to be found long after everything soft has gone. And yet, bone is not static. It is a living tissue, continuously remodeled by two populations of specialized cells working in coordinated opposition. Osteoclasts dissolve old bone, releasing calcium and other minerals into the bloodstream and creating small cavities in the bone matrix. Osteoblasts follow behind, filling those cavities with new bone material, laying down fresh collagen fibers that then mineralize into hard tissue. This cycle of resorption and formation happens continuously, throughout the skeleton, throughout a lifetime. The rate varies by age and by which part of the skeleton is being considered. In young children, the entire skeleton is replaced relatively quickly. In adults, the process slows but continues. The commonly cited estimate is that the adult human skeleton is substantially renewed over a period of approximately 10 years. Though this varies significantly by bone type, spongy bone inside vertebrae renews faster than dense cortical bone in the shaft of a long bone. This remodeling serves important functions. It allows bone to repair microscopic damage before it accumulates into fractures. It allows the skeleton to respond to mechanical load, becoming denser where stress is regularly applied. And it keeps the bone's mineral content available to the rest of the body, which draws on it constantly to maintain calcium levels in the blood. The skeleton you carry tonight is not the one you were born with, not the one you had 10 years ago, not the one you will have 10 years from now. It is the current version of a structure that has been continuously, quietly, rebuilding itself your entire life in the dark interior of your body, without ever asking you to notice. You are always, in the most literal sense, under construction, and the work is never finished, and never needs to be. The cosmic web and the branching inside your lungs follow the same mathematics, and the universe has been drawing this pattern since before breath existed. There is a geometry that appears again and again across scales so different they should have nothing to do with each other. The branching of rivers seen from above, the forking of lightning as it reaches for the ground, the structure of a leaf's veins, the network of blood vessels in a retina, the airways branching inside your lungs, dividing and subdividing from trachea to bronchi to bronchioles, to the tiny alveolar sacs where oxygen crosses into your blood, and the cosmic web itself, the largest structure in the known universe. Its filaments, branching and intersecting across hundreds of millions of light years. These patterns share a mathematical kinship. They are not identical, and the mechanisms that produce them are entirely different: gravity and dark matter in the cosmic case, developmental biology and fluid dynamics in the pulmonary case. But they belong to the same family of network geometries, optimized by different processes towards similar structural solutions: efficient distribution, maximum reach with minimum material, connection across scale. Researchers have formally compared the cosmic web and the human brain's neural network, finding statistical similarities in their clustering coefficients and degree of connectivity that are difficult to dismiss as superficial resemblance. A 2020 study by astrophysicist Franco Vazza and neuroscientist Alberto Folletti placed them side by side and found the comparison held up under quantitative analysis. The universe is not copying your lungs. Your lungs are not copying the universe. Both are following deep mathematical rules that produce similar solutions to similar problems across distances and scales that have no direct relationship. And yet, every breath you take moves through a structure that echoes the largest thing we know. The air that keeps you alive passes through a branching network that the universe has been drawing in different materials at different scales for as long as there has been anything to draw with. You breathe in a pattern the cosmos recognizes, and the cosmos, in its largest structures, traces a shape your body already knows. Somewhere in the universe, at every moment, a star is dying, and the death is a form of giving. Stars do not die quietly in the sense of disappearing without trace. They die generously. A star like our Sun, at the end of its life, will shed its outer layers in an expanding shell of gas called a planetary nebula, a glowing cloud of material that can extend for light years in every direction, illuminated by the hot remnant stellar core at its center. The material scattered into space by this process includes carbon, nitrogen, oxygen, and other elements forged in the star's interior over billions of years of fusion. More massive stars die more dramatically. A supernova releases more energy in a few seconds than our Sun will emit in its entire 10 billion year life. The explosion scatters the star's contents across light years of space at a significant fraction of the speed of light, seeding the surrounding interstellar medium with heavy elements that will eventually find their way into new clouds, new stars, new planets. In each case, the death is a distribution. The star takes what it has built over its lifetime and returns it to the universe, available now for whatever comes next. The elements in your body passed through this process. The carbon in every organic molecule you contain was scattered by a stellar death before it found its way, over millions of years and many intermediate steps, to you. Right now, somewhere in the Milky Way, a star is in its final hours or days or centuries. It does not know this. It is simply doing what stars do, right up until the moment it does something else. And what it does next will seed some small part of the galaxy with the material for whatever the universe still wants to make. Death, at stellar scales, is indistinguishable from generosity. The star gives everything back. It always does. The longest natural echo ever recorded lasted more than a minute, and it happened inside a space built by human hands for a different kind of resonance. Sound, When it enters a large enclosed space with hard, reflective walls, bounces. Each reflection is slightly quieter than the one before, as some energy is absorbed by the surfaces. The time it takes for a sound to decay to inaudibility after its source has stopped is called the reverberation time, and it varies enormously depending on the size of the space and the acoustic properties of its surfaces. In very large spaces with highly reflective stone walls, the reverberation time can be extraordinary. The Hamilton Mausoleum in Scotland holds a verified reverberation time of approximately 15 seconds, one of the longest of any building. Certain underground spaces, large caverns with hard rock walls, have produced even longer reverberations in informal measurements, with some claiming times approaching or exceeding a minute in ideal conditions. In these spaces, a single hand clap becomes something else entirely. The original sound is brief, sharp, immediate, but the echo that follows fills the space for seconds, then longer, layers of reflection overlapping and decaying in a slow, complex wash of sound that seems to come from everywhere at once. The original sound is long gone. What you hear is the space itself, remembering. There is a particular kind of awe available in a space with a very long echo, the sound of your own voice, returning to you slowly, from stone that has been standing for centuries. The room holding what you said, gently, for longer than you expected, giving it back to you in pieces, softer each time, until the last reflection falls below hearing and the silence returns, and you are left with the feeling of having been listened to by something very old and very patient. Stone remembers sound, briefly, softly, in a way that fades but does not rush its fading. Everything you have ever loved is made of atoms that will outlast the sun by trillions of years. The sun will exhaust its hydrogen fuel in approximately 5 billion years and end its life as a white dwarf, a slowly cooling remnant that will persist for trillions of years before cooling to darkness. The atoms that currently make up the sun will not be destroyed by this process. They will be redistributed, some remaining in the white dwarf, some scattered into the surrounding nebula, but the atoms themselves will continue to exist. Atoms are extraordinarily durable. Under ordinary conditions, a proton, one of the building blocks of atomic nuclei, is stable, essentially indefinitely. Theoretical physics suggests that protons may eventually decay, but the timescale for this, if it happens at all, is estimated at more than 10 to the power of 34 years, a number so vastly larger than the current age of the universe that it has no meaningful comparison in human experience. The atoms in the hand of someone you love, the atoms in a childhood home, the atoms in the first tree you ever climbed, in the first meal someone made for you with care. Those atoms existed before the solar system formed. They have been rearranged continuously by geological and biological and chemical processes across billions of years into the particular forms that mattered to you, and they will continue to be rearranged long after everything you know has changed beyond recognition. Nothing you have ever loved has been made of something temporary. The forms are temporary. The arrangements are borrowed, held briefly, and then returned. But the matter itself is ancient, and it is going nowhere, and the universe will carry it forward into a future so long it has no imaginable end. Love, it turns out, is made of some of the oldest and most durable material there is. The Aurora Borealis is the sun and the earth in conversation, and you can watch it written across the sky. The sun continuously emits a stream of charged particles, electrons and protons, and heavier ions, in what is called the solar wind. This wind flows outward from the sun in all directions, at speeds of several hundred kilometers per second, filling the entire inner solar system and beyond. Earth sits in this wind, and without protection, the charged particles would strip away the atmosphere and bombard the surface with radiation. Earth's magnetic field is that protection, generated by the motion of liquid iron in the planet's outer core. The geomagnetic field extends far into space, deflecting most of the solar wind around the planet in a teardrop-shaped region called the magnetosphere. The solar wind shapes the magnetosphere, compressing it on the sunward side and stretching it into a long tail on the night side. But at the poles, the magnetic field lines converge and dip toward the surface. And here, some of the solar wind's charged particles can funnel down along the field lines into the upper atmosphere. When they collide with oxygen and nitrogen atoms at altitudes of roughly 100 to 300 kilometers, those atoms are excited to higher energy states and then release that energy as light. Oxygen produces greens and reds. Nitrogen produces blues and purples. The aurora is light produced by the atmosphere itself, responding to the sun's touch. It is a conversation written in color across the upper sky, between a star 150 million kilometers away and a planet whose magnetic field is reaching up to meet it. Every aurora you have ever seen, or ever imagined seeing, was the Earth answering the sun, quietly, in color, across the dark. Water holds the memory of its shape, and ice remembers what it was before it became what it is. This is not mysticism, it is crystallography. Water molecules, when they freeze, arrange themselves into a hexagonal lattice structure determined by the geometry of the hydrogen bonds between them. The specific form this lattice takes, and therefore the specific shape of an ice crystal or snowflake, depends on the temperature and humidity conditions at the moment of freezing and throughout the crystal's growth. The crystal is, in a physical sense, a record of the conditions it formed under. When ice melts, the lattice dissolves and the water returns to its liquid form, the crystalline memory released. But the water molecules themselves are unchanged. The same H2O that was locked in a hexagonal lattice a moment ago is now flowing freely, carrying no visible trace of the structure it held. And yet the capacity to form that structure again is always present. Cool the same water under the same conditions, and it will form the same kind of crystal. The memory is not in the liquid water, but in the molecule itself, in the geometry of its bonds. Always available, always ready to reassemble into structure when the conditions allow. There is something in this that speaks to something broader. The capacity for structure, for pattern, for the particular shape a thing takes under particular conditions is not lost when the conditions change. It is held in potential, in the molecule, in the geometry that was always there. You have been many temperatures in your life. You have been liquid and you have been crystalline, open and settled, formless and structured. The capacity for each is always present. The conditions change and you respond to them. And the underlying geometry of what you are remains, patient and available, waiting for the right temperature to show itself again. Galaxies in clusters are threaded together by invisible bridges of hot gas, and the universe cannot stop connecting things. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies held together by their mutual gravity and embedded in vast clouds of hot, diffuse gas. This intracluster medium, as it is called, is not visible in ordinary light. It emits primarily in X-ray wavelengths, detectable only by space-based X-ray telescopes such as Chandra and XMM Newton. But between clusters, connecting them along the filaments of the cosmic web, there are bridges of gas even more diffuse and harder to detect. Called the warm-hot intergalactic medium, this gas fills the spaces between clusters and has until recently been extraordinarily difficult to observe directly because it is so thin and spread across such vast distances. Recent observations using stacked X-ray data from many galaxy pairs have begun to map these bridges, confirming their existence and measuring something of their properties. They are hot, between 100,000 and 10 million degrees, and they are thin, but they are there, threading clusters together like the strands of a web, carrying baryonic matter, ordinary, atomic matter along the filaments of the cosmic structure. The universe builds connections at every scale. Mycorrhizal networks thread trees together below the forest floor. Neural networks thread thoughts together inside the skull. River systems thread landscapes together into watersheds. And between galaxy clusters, in the largest structures the universe has made, invisible bridges of hot gas thread the cosmic web into something continuous, something that is, despite everything, connected. The universe does not make isolated things. It makes things, and then slowly finds ways to connect them. This appears to be a fundamental tendency, a preference, if the universe can be said to have preferences, built into the way structure forms at every scale. Nothing, in the end, is entirely alone. The connections are just sometimes very, very large. A single tree lifts hundreds of liters of water from the ground to its highest leaves every day, and it does this without a pump, without effort, without making a sound. A large tree on a warm summer day can move several hundred liters of water from its roots to its canopy through a process that requires no mechanical pump, no expenditure of energy in any conventional sense, and produces no sound audible to the human ear. The water moves upward through narrow tubes called xylem vessels, driven by a combination of forces that work together in a way that took botanists a long time to fully understand. At the top, water evaporates from tiny pores in the leaves, called stomata. This evaporation creates a tension, a slight negative pressure, that pulls the water column upward from below, the way a drinking straw works when you pull air from the top. The water column is held together by the cohesion of water molecules to each other and their adhesion to the walls of the xylem vessels. The tension is transmitted continuously down through the trunk, into the roots, drawing water up from the soil. This mechanism, called the cohesion tension theory, works because water under tension in the narrow xylem vessels does not break apart the way a stretched liquid would in a wider space. The vessels are narrow enough that the water column remains intact, even under significant negative pressure. The tree is, in effect, pulling the water upward by creating a continuous tension in a thread of liquid that stretches from root to leaf. On a hot summer afternoon, this is happening simultaneously in every tree, in every forest in the world. Billions of trees, quietly lifting water against gravity, leaf by leaf, root by root, moving a volume of water each day that would fill swimming pools, with no motor, no noise, no apparent effort. The quiet things are often doing the most extraordinary work. The tree does not announce what it lifts. It simply lifts it, all day, every day, in the unhurried way that living things do what they must. The universe was once small enough to hold in your hand, and has been expanding in all directions ever since that first, unimaginable moment. In the very early universe, before the first second had passed, before the first particle had fully formed, the entire observable universe, everything that would eventually become the hundreds of billions of galaxies we can detect today, was compressed into a region smaller than an atomic nucleus, smaller than a grain of sand, smaller than anything with a name in ordinary experience. This is not a comfortable image, and the mind does not settle easily into it. It is not that matter was crushed together in empty space. Space itself was that small. The entirety of what would become everything, including the space it would expand into, was contained in that first moment. There was no outside. There was no before, in any sense that physics can currently describe. Then it expanded, not exploded outward into existing space, expanded, space itself growing in all directions simultaneously, carrying matter with it, cooling as it grew, allowing first particles, and then atoms, and then clouds, and then stars, and then galaxies to form in its wake. The expansion has never stopped. It is still happening now, tonight, in every direction, at an accelerating rate, driven by the dark energy that fills the space between galaxies. The universe you inhabit tonight is the same universe that was once unimaginably small. The space between you and the nearest star is space that was not there at the beginning and has been growing, quietly and continuously, for 13.8 billion years. You are living inside something that is still becoming, still opening, still expanding outward from that first, impossible moment, carrying you gently with it in a direction that has no name because there is nothing outside it to name the direction from. The universe is still beginning. It has never stopped. In the deepest parts of the ocean, life invented its own sun, and it burns cold and blue and entirely alone. Below about 200 meters, sunlight fails entirely. The ocean below that depth is in permanent darkness, a darkness more total than any night on the surface, because there is no moon, no stars, no reflected glow from anywhere. In this permanent dark, at pressures that would crush any unprotected surface-dwelling animal, life did not give up. It found another way. Bioluminescence, the production of light by living organisms through chemical reactions, evolved independently in many different marine lineages. Bacteria, dinoflagellates, jellyfish, squid, fish, and countless other organisms produce their own light, using an enzyme called luciferase to catalyze a reaction between a molecule called luciferin and oxygen, releasing photons in the process. The light is cold, produced without significant heat, and is typically blue or blue-green, wavelengths that travel farthest through seawater. An estimated 76% of deep-sea animals produce bioluminescence. In the deep ocean, it is not the exception. It is the dominant form of light. Creatures use it to attract prey, to confuse predators, to find mates, to communicate in a darkness that has no other illumination. Some deep-sea fish carry bioluminescent lures dangling in front of their mouths. Some squid release clouds of bioluminescent fluid instead of ink, leaving a glowing confusion behind them as they escape. Some organisms flash in patterns as specific as a signature. In the permanent dark of the deep ocean, life looked at the absence of light and decided to make its own. Not dramatically, not as a grand gesture, but practically, biologically, over millions of years of quiet evolution. Because that is what life does. It finds what it needs, or it finds a way to make it. The deep ocean is full of small, cold, blue lights, burning in the dark, talking to each other in a language made of photons, in a world that the sun has never touched. The background radiation of the universe is so remarkably smooth and even that its small imperfections are the reason you exist. The cosmic microwave background, the oldest light we can detect, fills the entire sky with extraordinary uniformity. Its temperature, approximately 2.725 degrees above absolute zero, varies across the sky by only about 1 part in 100,000. These variations, called anisotropies, are tiny. On a map of the whole sky, they look like barely perceptible variations in color, a patchwork of regions fractionally warmer and fractionally cooler than average. These tiny imperfections are the seeds of everything. In the early universe, the regions that were slightly denser than average had slightly stronger gravity. That slightly stronger gravity attracted slightly more matter. Over hundreds of millions of years, those regions became denser still, eventually collapsing into the first stars and galaxies. The slightly less dense regions became the voids. The entire large-scale structure of the universe, every galaxy, every cluster, every filament of the cosmic web, grew from those tiny, ancient variations in the background temperature. If the early universe had been perfectly smooth, with no variations at all, gravity would have had nothing to amplify. Matter would have remained spread evenly through space. No clouds would have collapsed. No stars would have formed. No planets. No chemistry. No life. The imperfection is not a flaw in the universe. It is the universe's most important feature. The slight unevenness of that ancient light, the fractional variations in the afterglow of the Big Bang, are what made it possible for there to be a you in a particular place, on a particular planet, around a particular star, in a particular galaxy, feeling particularly sleepy on this particular night. You exist because the early universe was almost, but not quite, perfectly smooth. The tiny deviation from perfection became everything, including this. You are not traveling through space, so much as space is carrying you, and the distinction is one of the most quietly freeing ideas in physics. When we say the universe is expanding, We do not mean that galaxies are moving through space, like fragments from an explosion. We mean that space itself is stretching, growing between every point simultaneously. The way dots drawn on the surface of a balloon move apart from each other as the balloon inflates, not because the dots are moving across the surface, but because the surface itself is growing. This means that distant galaxies are not speeding away from us through space. The space between us and them is expanding, carrying them with it. The galaxies themselves, relative to the local space they occupy, may be nearly stationary. It is the medium, the space, that is in motion. The distinction matters for several reasons. It means that galaxies can recede from us faster than the speed of light, not because they are moving faster than light through space, which relativity forbids, but because the space between us is growing faster than light can cross it. The speed limit applies to motion through space, not to the expansion of space itself. It also means that you are not moving through the universe so much as being carried by it. The expansion of space carries the Milky Way, carries the solar system, carries the Earth, carries you, in a motion that is not traveling toward anything or away from anything, simply participating in the ongoing expansion of the whole. You are not going anywhere. The universe is growing around you, in all directions equally, at every moment, and you are at the center of that growing, as is every other point, as is everything. The universe does not take you anywhere. It simply opens, gently, in every direction, and takes you with it as it goes. Every sound ever made is still traveling outward through space, and the universe is keeping everything. Sound itself does not travel through space. As we noted earlier in our journey, it requires a medium, and the vacuum of interstellar space provides none. But sound is produced by vibrating matter, and vibrating matter produces electromagnetic radiation, and electromagnetic radiation does travel through space, essentially forever, unless it is absorbed by something. Every event that has ever produced light or heat or radio waves has sent those waves outward through space at the speed of light. The light from the first fire a human being ever lit is still traveling outward in an expanding sphere at 300,000 kilometers per second. It has been traveling for perhaps 400,000 years, and the wavefront of that ancient light is now 400,000 light-years from Earth, somewhere in the space between galaxies. The light from the first sunrise ever witnessed by a human eye. The thermal radiation from the meteor impact that ended the age of the dinosaurs. The radio waves from the first human radio broadcast. The light from the first nuclear detonation. All of it, expanding outward, at the speed of light, in all directions, forever, until it is absorbed by something or redshifted by expansion into wavelengths too long to carry meaningful information. The universe does not discard its history. It broadcasts it continuously, in all directions. Everything that has ever happened here is still, in the form of light and radiation, moving away from here at the maximum speed the universe allows. We are broadcasting, always, into the dark. We have been since the first warm thing glowed, in the first cold night. And the universe receives all of it, carries all of it outward, keeps all of it traveling, long past any memory of what it was. Nothing, in this deepest sense, is ever entirely gone. The oldest light we can detect is a glow that has been traveling since the universe was less than 400,000 years old, and it is still washing over you, right now. Tonight. The cosmic microwave background is not something that existed once and then faded. It is present everywhere, at every moment, in every direction. It fills the universe the way water fills the ocean, not in a particular place but as the medium itself. Every point in space is immersed in it. You are immersed in it, right now, as you rest. The photons that make up the cosmic microwave background were released approximately 380,000 years after the Big Bang, at a moment called recombination, when the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms for the first time. Before this moment, The universe was opaque. Photons could not travel freely because they were constantly scattering off free electrons. When recombination happened, the universe became transparent, and the photons that had been trapped were released, streaming freely in all directions. That release happened everywhere simultaneously. The photons that were released near our location in the early universe have long since passed us by, moving outward to distant reaches of the cosmos. The photons we detect now, as the cosmic microwave background, were released in regions that were, at the time of recombination, very far from where Earth would eventually form. They have spent 13.8 billion years traveling toward us, and they are arriving now, continuously, from every direction. The universe's oldest light is not a historical artifact stored somewhere. It is arriving, right now, passing through the walls of whatever room holds you, passing through you. The afterglow of the beginning, still warm enough to detect, still carrying information about what the universe looked like before stars existed, before planets, before any of this. The beginning has not finished arriving. It is still here, gentle and ancient, in the dark, all around you. Forests make their own weather, and the trees have been doing this longer than anything with lungs has been breathing. A forest is not merely a collection of trees that happens to occupy the same landscape. It is a system, a self-generating, self-regulating entity that actively participates in shaping the atmosphere above it. Trees transpire, releasing water vapor through their leaves into the air above the canopy. This water vapor rises, cools, and condenses into clouds. Those clouds produce rain. That rain falls back into the forest and is taken up by roots and eventually transpired again. This cycle, called the biotic pump, means that large forests can sustain rainfall far inland from the ocean, in regions that would otherwise be too dry to support them. The Amazon rainforest generates what researchers call flying rivers, enormous flows of water vapor moving through the atmosphere above the forest, carrying as much water as the Amazon River itself, distributing rainfall across vast regions of South America. The forest, in a very real sense, makes the rain that keeps the forest alive. When large areas of forest are cleared, the biotic pump weakens. Less water vapor enters the atmosphere, fewer clouds form, less rain falls. The remaining forest becomes drier and more vulnerable. The relationship between the forest and its weather is not passive. The forest is an active participant in its own climate, and when it is diminished, the climate it created is diminished with it. The trees have been making weather for hundreds of millions of years, long before the first bird flew through the clouds they created, long before anything walked beneath their canopy and looked up and felt the rain begin. The sky above a forest is partly made by the forest. The rain that falls on your face in the woods fell there partly because the trees asked for it, in the only language they have, which is water and patience, and the slow upward movement of life reaching toward light. Some stars spin so fast they have lost their roundness, and the universe holds shapes that geometry books forgot to mention. A perfect sphere is the natural shape of a large object held together by its own gravity, the form that minimizes surface energy and distributes gravitational force equally in all directions. Stars, like planets, tend toward spheres. Our sun is almost perfectly round, its equatorial diameter only about 10 kilometers larger than its polar diameter, across a total width of 1.4 million kilometers. That is a deviation of less than 0.001% from a perfect sphere, making it one of the most perfectly round natural objects ever measured. But not all stars rotate as slowly as our sun. Some rotate at extraordinary speed, completing a full rotation in hours rather than the approximately 25 days it takes the sun's equator to turn once. At these speeds, the centrifugal effect of rotation pushes material outward at the equator, flattening the star into an oblate spheroid, a shape like a slightly squashed ball, with a significantly larger equatorial diameter than polar diameter. The star Altair, one of the brightest stars in the night sky and part of the summer triangle, rotates so rapidly that its equatorial diameter is approximately 20% larger than its polar diameter. It completes one rotation in approximately 9 hours. If you could see Altair as a disk rather than a point of light, it would look noticeably flattened, like a star that has been gently pressed from above and below. The star Achernar, at the southern end of the constellation Eridanus, is even more extremely flattened, with an equatorial diameter roughly 56% larger than its polar diameter. It rotates so fast that its equatorial surface gravity is significantly lower than its polar surface gravity, and material at its equator is close to flying off entirely. The universe makes spheres when things are still, and when things spin, it makes something else, shapes that have no name in ordinary geometry, that exist only at the intersection of gravity and velocity, and the willingness of matter to become whatever the forces acting on it require. Everything finds its own shape, in the end, given its own particular motion. The atmosphere has no sharp edge, and the sky does not end so much as it quietly forgets to continue. If you were to travel upward from where you rest right now, the air would thin gradually, not abruptly. At sea level, the atmosphere presses down with the weight of the entire column of air above, approximately 10 kilometers of significant density, and then a much longer, much thinner tail extending upward. By the time you reach 5.5 kilometers, roughly the altitude of Everest Base Camp, you are above half the atmosphere by mass. At 100 kilometers, you reach what is called the Kármán line, the internationally recognized boundary of space, where the atmosphere is so thin that aerodynamic lift becomes impossible and orbital mechanics must take over from aerodynamics. But the atmosphere does not stop at 100 kilometers. It continues, growing thinner and thinner into the thermosphere and then the exosphere, where individual atoms and molecules follow ballistic trajectories rather than behaving as a fluid. The exosphere extends to perhaps 10,000 kilometers above the surface, before it grades imperceptibly into the solar wind and interplanetary space. There is no moment at which sky becomes space. There is only the gradual thinning of something into almost nothing, and then the almost nothing continuing for a very long time, and then, eventually, the medium of interplanetary space, which is itself not truly empty, but merely very, very thin. The sky above you tonight is not bounded. It continues upward from where you rest, thinning as it goes, through layers of increasing cold and decreasing pressure, past the altitude where weather happens, and the altitude where auroras glow, and the altitude where satellites orbit, and then farther, into the long, thin exosphere, and then into the solar wind, and then into the space between planets, and then between stars, and then between galaxies, in an unbroken continuum of decreasing density that has no edge, only a gradual, patient, endless thinning into the dark. The sky you breathe is the same sky that reaches to the stars. There is no wall between you and the universe. There never was. Even in the emptiest regions of space, something is always quietly happening, and the universe has never been completely still. Quantum mechanics, the physics of the very small, describes a universe in which the vacuum is not truly empty. Even in a region of space containing no particles, no radiation, no matter of any kind, the quantum vacuum fluctuates. Virtual particles, pairs of matter and antimatter, spontaneously appear and annihilate on timescales so short that they never violate the conservation laws of physics, because the energy borrowed to create them is returned almost immediately. These fluctuations are not theoretical conveniences, they are real, measurable effects. The Casimir effect, demonstrated experimentally in 1997, shows that two uncharged metal plates placed very close together in a vacuum experience a small attractive force caused by the fact that the quantum vacuum fluctuations between the plates are slightly suppressed compared to those outside, creating a tiny pressure difference. The vacuum is pushing the plates together because even nothing is doing something. Hawking radiation, the theoretical process by which black holes very slowly lose mass over astronomical timescales, also arises from quantum vacuum fluctuations near the event horizon. One virtual particle falls in, the other escapes, and the black hole loses a tiny amount of energy. The process is so slow for stellar mass black holes that it is entirely unmeasurable with current instruments, but the physics is considered robust. The universe has never been still, not in the moments after the Big Bang, when everything was fire and expansion, not in the cold reaches of intergalactic space, where the density of matter is lower than any vacuum achievable on Earth. Not in the darkness of this particular moment. While you rest and the world outside is quiet, something is always happening. At every scale, in every place, the universe is doing something. It cannot help it. It does not know how to stop. And in the most fundamental regions of space, where nothing else remains, the vacuum itself continues, quietly, persistently, endlessly fluctuating, as if stillness were the one thing the universe has never quite learned. And yet, for you, right now, this is close enough to stillness. The fluctuations are below hearing. The vacuum is far from here. And what you feel, in this room, in this quiet, is something that the universe has been working toward for 13.8 billion years, without knowing it was working toward anything at all. Rest is not nothing. It is the universe, in this one small place, arriving at something very close to peace. The night sky above you is not a view of the present. It is a mosaic of different pasts, all arriving at the same moment, and you are the point where all those different times meet. The star nearest to our Sun beyond the solar system, Proxima Centauri, is approximately 4.24 light-years away. The light you see from it left 4.24 years ago. The bright star Sirius, the brightest star in the night sky, is approximately 8.6 light-years distant. Its light left 8.6 years ago. Betelgeuse, the red supergiant in Orion's shoulder, is somewhere between 500 and 700 light-years away. Depending on the measurement method its light left in the medieval period, before Columbus, before the printing press, before anything you would recognize as the modern world. The Andromeda Galaxy, visible on a clear dark night as a faint smudge near the constellation Andromeda, is 2.5 million light-years away. What you see is the galaxy, as it was 2.5 million years ago, before Homo sapiens existed, before any human looked up at a sky and wondered what the faint smudge was. And the faintest objects visible to the naked eye and to the deepest telescopes are billions of light-years distant, their light carrying information from times before the Earth existed, before the Sun ignited, before any of the matter that makes you up had assembled itself into anything that could be described. All of this arrives at your eye simultaneously. On a single clear night, looking up, you receive light that departed from its sources across a range of billions of years, all converging on this one point, this one moment, this one pair of eyes open in the dark. You are not looking at the sky. You are the place where billions of years of different times meet and become a single moment of seeing. The universe, spread across 13.8 billion years of history, gathers itself into the width of a human gaze and calls it now. You have traveled a long way tonight, not in miles, not in any direction a map could show, but you have moved through something, through scale and time and the quiet astonishment of a universe that turns out to be more generous than it first appears. Rest here for a moment, before sleep takes you fully. Notice your breathing. It is slower now, perhaps, than when we began. The body has been listening this whole time, adjusting to the pace of the telling, settling the way water settles when the wind stops. Your breath is doing something tonight that it has done every night of your life without being asked. It is keeping you here, gently, without effort, without noise. The atoms in your chest, rising and falling, were forged in stars. The iron in your blood was scattered by an explosion that happened before this planet existed. The carbon in your bones was breathed out by ancient microbes into an atmosphere that was not yet ready for you, and held there patiently, for billions of years, until you arrived to breathe it back. You are not a visitor to the universe. You are a part of it that has become briefly, beautifully aware of itself. A place where the cosmos has folded inward and opened its eyes and looked around and felt, perhaps, something like wonder. Outside, wherever you are tonight, something is continuing. If there are trees nearby, their roots are moving water upward through the dark, slowly, against gravity, without sound. If there is a moon above the clouds, it is drifting, incrementally, along its ancient path, 3.8 centimeters farther from Earth than it was a year ago. If there is an ocean within reach of your imagination, tides are moving along its shores in response to a pull that has been operating since before the first fish swam. The cosmic microwave background is passing through the walls of your room right now. Ancient light from the universe's first breath, carrying the faint warmth of the beginning across 13.8 billion years to wash, gently and undetected, through everything you are. Somewhere in the Milky Way, in a cold cloud of gas and dust, a star is beginning to form. It will not ignite for another million years. It does not know you exist. And yet the atoms that will one day burn in its core were once in clouds that also made the sun, that made the warmth, that made the food, that made the body that is now, tonight, growing heavy with sleep. Everything is connected. Not metaphorically. Not as a comfort offered without evidence. Literally, materially, traceable, in the actual movement of actual atoms across actual billions of years. The connection is real. You are held by it. You have always been held by it. You were held by it before you knew there was anything to be held by. Let the weight of your body settle now into whatever holds it. The universe is 13.8 billion years old, and it has spent every moment of that time becoming the kind of place where something like you could exist, in a room like this, on a night like this, feeling exactly this. That is not an accident. That is not nothing. That is the universe, arriving, after all this time, at one of its own quiet conclusions. The stars are still out there, burning in the dark, patient and ancient and entirely unconcerned with hurry. The deep ocean currents are still moving, slowly, along the seafloor, carrying cold water from one century into the next. The mycorrhizal networks in the nearest forest are still threading their slow chemical conversations through the dark soil. And you are here, breathing, warm, held by gravity, by atmosphere, by the accumulated generosity of everything that came before you and made a place for you to land. There is nothing you need to do right now, nothing you need to remember, or solve, or carry forward into the next moment. The next moment will arrive on its own, the way the next moment always has, without any help from you. For now, there is only this: the slow breath, the quiet room, the ancient light passing through the walls, the universe, vast and still and continuous, holding you in the only way it knows how, which is completely and from every direction, and without ever letting go. You are made of stars. You are resting on a living planet. You are breathing air made by ancient life and held in place by a magnetic field generated in the liquid iron heart of the world beneath you. You are, in every measurable sense, exactly where you are supposed to be. Let your eyes close, if they haven't already. Let the breath slow a little more. Let the weight of everything you learned tonight settle gently, like dust settling in a room after a long day, finding its place, growing still. The universe will continue while you sleep. It always does. The stars will turn above the clouds. The deep currents will move below the waves. The ancient hum of the cosmic background will wash through everything, quiet and constant. The oldest lullaby there is, still playing, as it has always played, in every direction, for everyone and no one, for as long as there has been a universe to fill with its gentle, ancient light. Sleep now. The cosmos has you. I hope you sleep well and dream softly. Good night.